At the center of our Milky Way galaxy, hidden behind clouds of dust and stars, lies something we cannot see with our eyes, but which has the mass of millions of suns. This mysterious object is called Sagittarius A-star, and it's a supermassive black hole. Unlike the monsters powering distant quasars and active galaxies, Sagittarius A-star barely makes a peep, but its silence is misleading. Just beneath the surface, there's a storm of magnetic fields, flares, and extreme gravity that stretches the limits of physics. This is the story of how we discovered it, how we photographed the unseeable, and what this black hole has taught us about the universe. The galactic bulge that hid the truth. For a long time, even after people began building telescopes and studying the stars with scientific tools, the center of the Milky Way remained hidden. Astronomers could map parts of the sky, track planets, and chart the motion of stars, but something was still in the way. Whenever they turned their instruments toward the thickest part of the Milky Way, toward the constellation Sagittarius, they ran into a wall of light and shadow, of gas and dust, and of stars packed so tightly that they blurred into each other. This area, now known as the galactic bulge, is one of the most crowded regions in the entire Milky Way. It is a huge central swelling made of hundreds of billions of stars. From Earth, it lies in the direction of the galactic center, but seeing through it is not easy. In fact, for centuries, it was nearly impossible. When people look up at the Milky Way with the naked eye, they see a pale band stretching across the night. It looks almost like a faint cloud. But that band isn't made of cloud or mist. It's made of stars. So many stars packed so close together that they blend into a soft glow. That glow gets brightest near the center of the Milky Way. But along with the brightness comes something else. Darkness. This darkness is not the absence of stars. It's the presence of dust. All across the galaxy, floating between stars, are clouds of interstellar dust. These clouds are made of tiny particles, bits of carbon ice and rock, left over from older stars and drifting slowly through space. While these particles are small, they're spread out over such huge distances that they can block light, especially visible light, the kind our eyes and early telescopes can see. That's the key problem. For most of history, telescopes worked only in visible light. They were built like giant eyes, collecting light from stars and focusing it into images. But visible light is easily blocked. When it tries to pass through dust, it gets scattered or absorbed. And nowhere in the sky is there more dust than in the direction of the galactic center. Astronomers would look towards Sagittarius and see nothing but confusion. A thick mess of stars broken up by dark streaks like smoke smeared across the sky. The stars closer to Earth were visible, but behind them, darkness. The light from the true center of the galaxy couldn't reach us. It was as if someone had drawn a curtain across the middle of the Milky Way. And the bulge itself made things worse. Unlike the flat disk of stars that stretches out like a pancake around the galaxy, the bulge is swollen and round. It's thicker and denser than the outer regions. Stars in the bulge are packed closely together, overlapping and shining in all directions. But because there are so many of them, and because of all the dust mixed in, their light becomes hard to separate. The signals are there, but they get lost in the noise. This made the center of our galaxy one of the most mysterious places in the sky. People could see the outer arms of the Milky Way, and they could map stars in nearby regions, but they couldn't see what lay at the heart. They didn't even know if there was a heart. Was the galaxy spinning around something? Was there a true center at all? Or was it just a loose collection of stars with no fixed point? Some early astronomers believed the Sun was near the center of the Milky Way. When they looked around, they saw stars in every direction, so they guessed we must be somewhere near the middle. But that was only because they couldn't see past the dust. Their view was blocked in the direction of the real center, so it looked like the stars were evenly spread out. In the 18th and 19th centuries, astronomers like William Herschel tried to map the shape of the Milky Way. Using star counts, simply counting how many stars were visible in different directions. they tried to figure out the structure of the galaxy, but they didn't know about interstellar dust. So when their maps showed more stars in some directions and fewer in others, they assumed that meant the galaxy was shaped unevenly. In truth, the dust was hiding much of what they needed to see. It wasn't until the 20th century that things began to change. New kinds of telescopes were developed, ones that didn't just use visible light. Scientists realized that if they wanted to see through the dust, they needed to use forms of light that could pass through it more easily, like infrared and radio waves. These types of light are invisible to our eyes, but they carry information just like visible light does. And unlike visible light, they can travel through dust without being scattered or absorbed as much. With infrared telescopes, astronomers could finally start to peer into the galactic bulge. They could see stars hidden behind the clouds. They could begin to map the true shape of the center. And with radio telescopes, they picked up signals from deep within the galaxy, waves of energy coming from strange sources that had never been seen before. One of the most important discoveries came in the 1930s and 1940s, when radio astronomers started detecting a strong signal coming from the constellation Sagittarius. It wasn't a normal star, and it didn't look like anything familiar. It was a powerful source of radio waves, coming from the very center of the Milky Way. They called it Sagittarius A. At first, it was just a bright spot in radio images, buried deep inside the galactic bulge. But over the years, as instruments improved and scientists studied the region more closely, they began to realize that something very strange was there, something massive, something invisible, and something pulling stars around it at incredible speeds. But even then, the dust and gas made the study of the galactic center difficult. Astronomers had to build better and better instruments, working from mountaintops, balloons, and eventually space to get clearer views. The bulge remained one of the most crowded, chaotic, and complex places in the galaxy. What made it even harder was that stars in the galactic bulge move fast. They're not slowly drifting. They're whipping around the center in tight, fast orbits. Tracking those motions requires extreme precision. You have to watch the same stars for years, taking careful measurements to understand their paths, and only then do the patterns begin to appear. All this, the dust, the density, the movement, combined to keep the truth hidden for most of human history. While ancient people made up stories and early scientists guessed at shapes, the real center of the Milky Way remained blocked by its own structure. It was there all along, behind a glowing, swollen mass of stars and a thick fog of interstellar material. Only by looking with new kinds of eyes could we begin to see it for what it really was. The radio signal that changed everything. In the early 1930s, a young engineer named Carl Jansky was working at Bell Telephone Laboratories in New Jersey. His job had nothing to do with astronomy. He was simply trying to solve a problem for long-distance radio communication. At the time, radio was growing fast. Ships, stations, and countries all depended on clean signals. But there were strange background noises, static that couldn't be explained. Jansky was asked to find out where these noises were coming from. To do this, he built a strange-looking machine. It was a large, rotating antenna. Some called it a merry-go-round because it sat on wheels and could be turned to face different parts of the sky. It was designed to pick up radio waves in the shortwave band, around 20.5 megahertz. That's much lower in frequency than visible light, but it carries useful information for communication. Jansky spent months collecting data. He found that some of the static came from nearby thunderstorms. Some came from distant lightning. But there was one source of noise that came and went in a regular pattern, about once every 24 hours. At first he thought it must be related to the sun, but over time the timing didn't match exactly. It came roughly 4 minutes earlier each day. That's when he realized this source wasn't tied to the Earth's rotation relative to the sun. It matched the Earth's rotation relative to the stars. In other words, it was coming from space. The direction of the signal pointed toward the center of the Milky Way. This was the first time anyone had ever detected radio waves from outside the solar system. It was an accident, a side effect of routine engineering work. Jansky's discovery was the beginning of radio astronomy. At first, the news didn't cause much excitement. Astronomers were still focused on optical telescopes, and few understood the importance of radio signals from space. Jansky himself didn't continue with space research. Bell Labs moved on to other projects, and his antenna was eventually dismantled. But his discovery had planted a seed. A few years later, a man named Grote Reber picked up where Jansky had left off. Reber was a radio engineer and amateur astronomer. He read about Jansky's work and decided to build his own radio telescope in his backyard. He constructed a large parabolic dish, about 9 meters across, and began scanning the sky for radio waves. Reber confirmed Jansky's results and mapped the radio sky for the first time. His maps showed strong radio signals coming from the same part of the sky. Through the 1940s and 1950s, more scientists joined the field. Radio astronomy started to grow. New antennas were built, larger, more sensitive, and able to cover a wider range of frequencies. These instruments revealed a sky that was invisible to the eye. Objects that looked dark in visible light sometimes glowed brightly in radio waves. The center of the Milky Way, once hidden behind dust, now began to speak in a new language. By the 1960s, radio telescopes had become powerful tools. Scientists could study the structure of the galaxy in detail. They detected radio signals from gas clouds, supernova remnants, and even from other galaxies. But one spot remained especially interesting: the strong, compact radio source in the direction of Sagittarius. This signal, first noticed by Jansky, was coming from a very specific point. It was steady, strong, and located right at the heart of the Milky Way. It didn't flicker, and it didn't spread out over the sky. It was compact, confined to a very small area. That suggested it was coming from something small, but incredibly powerful. But even in the 1970s, no one knew exactly what it was. The signal was strong, but it wasn't easy to explain. It didn't match the patterns of known nebulae. It didn't look like a supernova remnant. To learn more, astronomers needed to watch how stars moved around this invisible point. But this kind of research took time. The center of the Milky Way is 26,000 light-years away. Stars there move quickly, but not so fast that their orbits can be tracked in just a few days or weeks. Infrared eyes open in a dusty darkness. In the second half of the 20th century, scientists began building instruments that could detect infrared light from space. Some of the earliest attempts were made using high-altitude balloons and aircraft. Earth's atmosphere absorbs a lot of infrared light before it reaches the ground. If you want to study the sky in infrared, you need to get above the thickest parts of the atmosphere. One of the key steps was putting infrared telescopes on mountaintops. In places like Mauna Kea in Hawaii or the Atacama Desert in Chile, the air is dry and thin. That makes it easier for infrared light to reach the instruments. From these high points, astronomers began collecting the first clear images of stars and gas clouds hidden in the center of the Milky Way. Even early results were surprising. In regions that looked dark in visible light, infrared telescopes revealed clusters of stars. The heart of the galaxy was not empty, it was full of activity. What had once been a blank patch of sky now came to life. Still, ground-based telescopes had limits. The Earth's own heat and atmosphere made it difficult to get clear, uninterrupted data in certain infrared wavelengths. The next step was to go into space. In 1983, NASA launched the Infrared Astronomical Satellite, or IRAS. It was the first telescope to map the entire sky in infrared. Though not focused only on the galactic center, it showed just how much was hidden in the dusty parts of the sky. Whole regions that seemed empty in optical images lit up in the infrared, filled with young stars, warm dust, and strange sources of heat. Later space telescopes like the Spitzer Space Telescope, launched in 2003, would go much deeper. spending years looking into these hidden regions. Spitzer was especially important. With its sensitive instruments cooled to very low temperatures, it could pick up faint heat signatures from across the galaxy. One of its targets was the center of the Milky Way. Using its infrared eyes, Spitzer saw stars swirling close to a dense, invisible spot. This point, already known from radio signals as Sagittarius A-star, was now under observation in a new way. While Spitzer worked from space, ground-based infrared telescopes were improving too. In Chile, at the European Southern Observatory's Very Large Telescope, a team led by Reinhard Genzel spent years tracking the motion of stars near the galactic center. At the same time, in Hawaii, another team led by Andrea Ghez used the Keck Observatory to do the same thing. They used advanced infrared cameras to pierce the dust and follow the paths of individual stars so close to the black hole that they completed orbits in just a few years. These stars, called S-stars, became key to proving what lay at the center of the Milky Way. One of them, named S2, moves in a long, fast orbit that brings it extremely close to Sagittarius A-star. By watching its path over time, both research teams were able to calculate the mass of the object pulling on it. The result was stunning. The object had the mass of about 4 million suns, but it was packed into a space smaller than our solar system. It didn't emit light like a star. It was, almost certainly, a supermassive black hole. None of this would have been possible without infrared astronomy. The dust around the galactic core still blocked visible light, but in the infrared, the story became clear. Stars danced around an invisible force. Heat glowed where the eye saw nothing, and the shape of the galaxy's hidden center began to emerge. The stellar dance that gave away the secret. With the right tools, the movements of stars can be measured down to a fraction of a second of arc, a tiny angle in the sky, but enough to reveal dramatic stories when you're watching something over years or even decades. In the 1990s, a group of astronomers began doing just that. One of the teams was led by Reinhard Genzel, working out of the Max Planck Institute in Germany. Another was led by Andrea Ghez at UCLA in California. Each team used powerful ground-based telescopes fitted with advanced imaging systems to peer through the thick dust of the galactic center. Even with infrared telescopes, the challenge was immense. Earth's atmosphere creates constant interference, blurring images and making stars appear to shimmer or move randomly. To deal with this, astronomers used a technology called adaptive optics. It allowed the telescopes to adjust in real time, cancelling out much of the distortion caused by the air above. Near Sagittarius A-star, they found stars moving at incredible speeds. These stars were whipping around a point in space like comets flying past a campfire. Some traveled at over 5,000 kilometers per second. That's fast enough to go from Earth to the Moon in just over a minute. The key breakthrough came from watching these stars over time. One in particular, known as S2 or sometimes S02, stood out. It was a bright star, moving in a tight, fast orbit around a completely dark region of space. Over the course of just 16 years, S2 completed a full loop. No star this close to the center had ever been tracked for so long with such precision. S2 followed an elliptical path, just like planets do around the Sun. That meant it was responding to gravity. From the orbit of S2 and other nearby stars, astronomers could calculate the mass of whatever was pulling on them. The answer was staggering: over 4 million times the mass of our Sun, all packed into a region smaller than our solar system. This left only one explanation: a black hole. Not just any black hole, but a supermassive one. It was the closest evidence we'd ever had of such an object. Black holes had been suspected and theorized for decades, but most of the time, they had only been studied indirectly through X-rays from distant galaxies or simulations on computers. Here, for the first time, scientists were watching stars orbit around one, real stars moving in real time around something truly invisible. The evidence grew stronger with every passing year. More stars were tracked, some had longer orbits, some were even closer than S2. All of them pointed to the same central object. And even more, the orbits behaved exactly as predicted by Einstein's general theory of relativity. Their paths showed subtle changes, slight shifts in timing and direction that couldn't be explained by Newton's laws alone. This meant that the gravity near Sagittarius A-star was not only strong, it was warping space and time itself. In 2002, Andrea Gheze's team published the first full orbit of S2. In 2008, Reinhard Genzel's group followed up with even more precise measurements. The results were nearly identical. Both teams, working independently on opposite sides of the world, had reached the same conclusion. There was a massive, invisible object at the center of our galaxy. Its gravitational pull was shaping the motion of nearby stars. It could be nothing else but a black hole. As technology improved, observations became even sharper. By the 2010 S, telescopes were capturing positions down to thousandths of a second of arc. That's like measuring the width of a human hair from several kilometers away. And these measurements kept confirming what we already knew. Sagittarius A-star was real. It shaped the space around it. It was a black hole. And yet, in all this time, we still had not seen it, not directly. We had watched the stars move. We had followed the invisible footprints, but the black hole itself remained unseen. It would be some time before we found a way to look even closer. Different breeds of darkness, from primordial to supermassive. When scientists first began to understand black holes, they were not looking at just one type of object. The idea of a black hole is simple in theory. A region in space where gravity is so strong that nothing, not even light, can escape. But the ways in which such objects form, grow, and behave can be very different. This is why astronomers often talk about types or classes of black holes. The one at the center of our galaxy, Sagittarius A-star, belongs to the largest known class, supermassive black holes, but it is far from the only kind. Understanding the others helps explain just how unusual our galactic center really is. The smallest known black holes are called stellar mass black holes. These are the remains of massive stars that reach the end of their lives in violent explosions called supernovae. When a star several times heavier than the Sun burns through all its fuel, it no longer has the energy to push back against gravity. The core collapses, and if the mass is high enough, it becomes a black hole. These objects are small on a cosmic scale, sometimes only a few kilometers across, yet they hold more mass than our Sun. Despite their size, they can have powerful effects on their surroundings, especially if they pull material from a nearby star, forming an accretion disk that shines in X-rays. These stellar black holes are scattered throughout galaxies, including our own, and astronomers have found dozens of them through careful observation of such energetic emissions. A step up from these, though much harder to find, are intermediate mass black holes. These range from hundreds to thousands of times the Sun's mass. Their origins are not fully understood. Some theories suggest they could form from the merger of multiple stellar black holes inside dense star clusters. Others suggest they might grow by steadily consuming gas and stars over long periods. They are rare in observation, which makes them interesting. Intermediate black holes may represent a missing link in the growth process between stellar mass and supermassive black holes. If these mid-sized objects are truly out there in large numbers, they might be the seeds that later grow into the giants we see at the centers of galaxies. Then there are the true giants, the supermassive black holes. These weigh millions to billions of times the Sun's mass. Sagittarius A-star is on the lighter side for this class, but even that makes it unimaginably powerful. Unlike stellar black holes, which form from single stars, supermassive black holes could not have formed in one sudden collapse. They must have built their mass over time, possibly beginning with the collapse of enormous clouds of gas in the early universe, or from mergers between smaller black holes and star clusters. Almost every large galaxy appears to have one of these giants at its core, and they play a major role in shaping their galaxy's evolution. There is also a type that exists only in theory: primordial black holes. These would have formed not from stars, but from extreme density fluctuations in the very early universe, just moments after the Big Bang. The idea is that tiny regions of space could have been so dense that they collapsed directly into black holes, some no bigger than an asteroid, others potentially much larger. If they exist, they could be scattered everywhere, perhaps even passing through our solar system from time to time without being detected. Some scientists have even proposed that certain unexplained cosmic phenomena could be the result of such ancient black holes. Another interesting theoretical type is the ultramassive black hole, an extension of the supermassive category. These would have masses exceeding 10 billion suns, and a few candidates have been observed in the centers of extremely large galaxies. Their size raises questions about how fast black holes can grow and whether there's a natural limit to their mass. Sagittarius A-star is firmly in the supermassive category, but it has some unique qualities. Compared to the largest black holes in the universe, it is relatively quiet. Many supermassive black holes are active, consuming huge amounts of material and producing blazing jets of energy that can be seen across cosmic distances. Our galactic center is currently in a low-activity phase, feeding only occasionally and producing brief flares in radio, infrared, and X-ray wavelengths. This quietness makes it harder to study in some ways because it does not have the bright, obvious emissions that active galactic nuclei produce. Yet it also makes it an ideal laboratory for studying the black hole itself, without interference from the chaos of extreme feeding events. By comparing Sagittarius A-star to other black holes, scientists gain perspective on its role in the galaxy. Stellar black holes might be more common, but their influence is local. They affect only their immediate surroundings. Intermediate black holes could bridge the gap, but they are rare in detection and uncertain in origin. Supermassive black holes shape entire galaxies, holding them together with their immense gravity and influencing the movement of stars and gas far beyond their event horizons. And if primordial black holes exist, they could provide clues about the earliest moments of the universe, though finding them would be far more difficult than tracking the massive object at the center of our own Milky Way. All of these types, from the smallest stellar remnants to the most colossal supermassive cores, share one unifying trait: their gravity is absolute. Once anything crosses their event horizon, it is gone from the observable universe. Yet their differences paint a picture of cosmic diversity within the category of black hole. This diversity is why astronomers do not simply study Sagittarius A-star in isolation, but instead place it in the larger context of black hole research. It helps us see what is typical and what is unusual about our galactic center. How Sagittarius A got its star. From Earth's position inside the Milky Way, we can't look down at our galaxy from above. We're stuck inside it, surrounded on all sides. So to talk about different regions of the galaxy, astronomers use constellations as directional signposts. When they say something is in Sagittarius, they mean it lies in the sky within the area of that constellation. It doesn't mean the object is part of the constellation, just that it's in the same region of the sky. When astronomers looked closer in the direction of Sagittarius with their radio telescopes, they realized they were seeing a cluster of different sources, all located near the center of the Milky Way. To keep track of these signals, they needed names. Astronomer Bruce Ballack and his colleague Robert Brown were studying the central radio source in the early 1970s, using high-resolution radio imaging. They were zeroing in on a compact point at the very heart of this group. They called the whole group Sagittarius A, since it was the first major radio source found in that region. Following the naming tradition used in radio astronomy at the time, A stood for the first discovered object in the constellation Sagittarius that gave off radio waves. If more sources were found nearby, they would be called Sagittarius B, Sagittarius C, and so on. Within Sagittarius A, Ballack and Brown identified a point that looked, as far as their equipment could tell, like a central engine, maybe the core of the entire Milky Way. That's when they gave it its unusual name, Sagittarius A-star, written with an asterisk at the end. At the time, Balick and Brown were using a coding style borrowed from atomic physics. In those fields, the asterisk was sometimes added to indicate an excited state, a version of an atom or particle that had more energy than usual. It wasn't a formal naming rule in astronomy, but it felt right. Sagittarius A was more intense, more concentrated, and more mysterious than the rest of Sagittarius A. The asterisk was their way of pointing that out. The name stuck. In the years that followed, as astronomers across the world focused more and more on this strange spot at the center of the Milky Way, the name Sagittarius A-star became standard. It showed up in papers, telescope logs, and research reports. Even as technology advanced and scientists grew more confident that this object was a black hole, millions of times more massive than the Sun, the name remained. In a way, it's ironic. The asterisk, read aloud as star, sits at the end of the name for an object that isn't a star at all. Sagittarius A-star doesn't give off its own light in the usual way. It pulls light in, it bends space, it swallows anything that gets too close, and yet the name gives this invisible thing a place in the map. Astronomy is full of these names. Some, like Betelgeuse or Vega, come from ancient languages. Others, like M31 or NGC 2392, are catalogue numbers, codes given by people trying to list thousands of objects without using poetic titles. When scientists discover something new, especially something not visible to the naked eye, they often fall back on a mixture of tradition, convenience, and a little creativity. Radio sources, for example, are usually named by location and order of discovery. Pulsars, spinning neutron stars that send out regular radio pulses, are often labeled with their coordinates like PSRB 1919 plus 21. Galaxies in catalogues are given numbers: Messier 87, NGC 5128, and so on. Sometimes the names are beautiful, sometimes they're just practical, but in every case, they help scientists keep track of what they're studying. In the case of Sagittarius A-star, the name does more than mark a spot on the sky. The name may be simple, but that one small mark, a single asterisk, carries the weight of a galaxy. Why does every galaxy have one? The supermassive puzzle. Almost every galaxy, no matter its size or shape, seems to have a giant black hole at its core. The same kinds of massive gravitational anchors appear at the heart of spirals, ellipticals, and even many irregular galaxies. Some are bigger than Sagittarius A-star, some far smaller, but the common thread is clear. This is a rule of the universe. The first hints of this came from galaxies where the central region was unusually bright. These active galactic nuclei were giving off enormous amounts of radiation. They were so powerful that no ordinary cluster of stars could explain them. The most convincing explanation was that a supermassive black hole was feeding on gas and dust, releasing energy as the material spiraled inward. This same reasoning applied to quasars, the brilliant beacons seen billions of light years away, which are now understood to be powered by black holes weighing millions or even billions of times the mass of our Sun. Once astronomers had the right tools, they began searching for signs of these central giants in more ordinary galaxies. Time after time, the evidence showed they were there, even in galaxies that were quiet and dim at the center. In some cases, the black hole was dormant, not actively consuming much material, but its gravitational pull was still measurable through the motion of nearby stars and gas clouds. It soon became difficult to find a galaxy that didn't have one. The question then shifted from, does our galaxy have a supermassive black hole, to why does every galaxy seem to have one? The simplest answer would be that these black holes formed alongside their galaxies, perhaps as a natural part of galaxy formation. One idea is that in the very early universe, clouds of gas collapsed not into stars, but directly into massive black holes, which then grew over billions of years by swallowing matter and merging with other black holes. Another possibility is that the first stars, enormous ones far larger than any that exist today, lived short, violent lives and collapsed into massive seeds, which in turn grew into supermassive black holes. A key part of the puzzle is the strange link between the mass of a galaxy's central black hole and the mass of the galaxy's bulge, the dense central region of stars. Even in galaxies far apart in size, this relationship holds with surprising precision. This suggests that black holes and galaxies influence each other's growth. If the black hole feeds aggressively, it can produce winds and jets that push gas away, slowing star formation in the galaxy. If the galaxy forms more stars, more material might eventually fall toward the center, feeding the black hole. This two-way relationship hints at a deep connection in their evolution, but no one fully understands how it works. The timeline of formation is also murky. Astronomers have found quasars powered by billion solar mass black holes when the universe was less than 1 billion years old. That means these monsters formed incredibly quickly, far faster than current models would suggest. To grow that large in such a short time, something unusual must have happened. Perhaps an early phase of rapid matter collapse or a series of frequent mergers between smaller black holes. Sagittarius A-star is relatively small. The black hole in the galaxy M87, for example, weighs in at several billion solar masses. And yet, despite the difference in scale, Sagittarius A-star fits into the same cosmic pattern. Its presence tells us that even a relatively modest galaxy like ours still carries this massive object at its core. Some researchers have wondered whether it's even possible to have a galaxy without a supermassive black hole. There are a few candidates, small, faint galaxies where no central black hole has been detected, but the limits of current technology mean we might simply be missing them. It could be that these galaxies have black holes so small or inactive that we cannot yet see their effects. The deeper we look, the more it seems that these central giants are fundamental to the life story of galaxies. They may act as regulators, controlling the flow of gas, the rate of star formation, and even the shape of their host galaxies. In some ways, they might be thought of as engines, driving the large-scale structure of the universe. In others, they are more like silent governors, influencing events without always revealing themselves. The fact that we don't know exactly how they first appeared means that the story of galaxy and black hole formation is still incomplete. Were they born together, side by side in the first cosmic dawn, or did the black holes come later, carved out of the first generation of stars? The evidence points in several directions at once. By observing Sagittarius A-star in detail, we can test theories about black hole growth, galaxy evolution, and the strange balance that seems to exist between a galaxy's stars and its hidden heart. Every insight we gain here might help explain the same structures in far more distant galaxies, where the light has traveled billions of years to reach us. Even with decades of study, the supermassive puzzle is far from solved. We now know the scale of the mystery, and that in itself is a kind of progress. But each new discovery about these cosmic giants raises new questions about where they came from and why the universe seems to insist on placing one in almost every galaxy it makes. Sagittarius A-star versus the giants of the cosmos. If Sagittarius A-star replaced the Sun in our solar system, its event horizon would swallow Mercury, Venus, Earth, and Mars, and we wouldn't even have time to notice before everything went dark. But in the realm of the universe's largest black holes, Sagittarius A-star is not the king of the mountain. It's not even close. Take the black hole at the center of the galaxy, M87. The same one famously imaged by the Event Horizon Telescope in 2019. This black hole is about 6.5 billion solar masses, over 1,600 times the mass of Sagittarius A-star. It's big enough to fit our entire solar system, including the Oort cloud, well within its event horizon. Despite its enormity, M87's black hole is not even in the running for the largest ever found, showing just how wild the size spectrum of these objects can be. Then there's Holm 15A star, a central black hole in a galaxy cluster more than 700 million light-years away. This one has been estimated to weigh in at around 20 billion solar masses. It sits in the middle of a galaxy that itself is the largest ever found, with a sprawling halo of stars. If Sagittarius A-star were to somehow be swapped with Holm 15 A-star, the gravitational changes would reshape the entire Milky Way. The orbits of stars would shift dramatically, and the central bulge would become much denser and brighter from the intense gravitational pull. And then there's Ton 618. This monster is one of the largest known black holes in the universe, and it makes Sagittarius A-star look like a pebble beside a skyscraper. Estimates place Ton 618's mass at around 40 billion times that of our Sun. To put that into perspective, you could line up over 10,000 black holes the size of Sagittarius A-star before you'd match its mass. Ton 618's event horizon is so vast that light would take about a week to travel across it, compared to about 24 seconds for Sagittarius A-star. The scale is beyond everyday comprehension. What's interesting is that, even though these black holes are so much bigger, they may not be dramatically more dangerous in their immediate environments. A black hole's pull only becomes overwhelming close to it. Outside that zone, its gravitational influence is just like any other object of the same mass. In other words, if our Sun were magically replaced by a black hole of equal mass, Earth's orbit would remain unchanged. It would just be very, very dark and cold. The same is true on the scale of galaxies. A bigger black hole doesn't mean it's gobbling up stars by the millions each day. It just has the potential to if something strays too close. The difference is in how these black holes grow and how active they become. Sagittarius A-star is relatively quiet. It feeds on small amounts of gas and dust, producing weak flares of X-rays and radio waves now and then. In contrast, something like Ton 618 is an active quasar, meaning it's devouring matter at a tremendous rate. As material falls toward it, it forms a blindingly bright accretion disk, outshining entire galaxies. This intense feeding frenzy not only powers its brightness, but also allows it to grow even larger over cosmic time. Astronomers think that Sagittarius A-star may have once been much more active in the distant past. Evidence suggests that millions of years ago, it could have flared brightly enough to send powerful radiation sweeping across the Milky Way. Some remnants of that activity might still be visible today, such as the mysterious Fermi bubbles, enormous lobes of gamma-ray emission extending above and below the galactic plane. If true, Sagittarius A-star might have been more like a small-scale quasar in its youth before settling into its current quiet phase. When comparing these cosmic giants, scientists also look at how quickly they spin. The spin of a black hole can influence how it pulls in matter, how it shapes jets of particles, and how its surrounding space is warped. Sagittarius A-star's spin is still being measured with great care, but some of the larger black holes, like M87S, are believed to spin close to the maximum possible rate allowed by physics. This rapid spin can act like a cosmic blender, whipping up surrounding material and launching it into space at near light speeds. Ton 618's spin is less certain, but given its size and activity, it likely has a powerful rotational energy reservoir. Sagittarius A-star could have started as a smaller black hole that steadily grew by eating gas, dust, and unlucky stars. But Ton 618 and Holm 15 A-star must have had a head start. Some suspect they formed from the collapse of enormous gas clouds. Others think they grew through multiple mergers with other black holes during galaxy collisions. Sagittarius A-star probably gained some of its mass this way too. The Milky Way has had a history of merging with smaller galaxies, each potentially bringing its own central black hole. Over billions of years, these central objects could have sunk toward the center and merged with Sagittarius A-star, adding to its mass. While it's unlikely our galaxy will ever host a black hole as large as Ton 618, future mergers, including the eventual collision with the Andromeda galaxy, will give Sagittarius A-star a growth spurt. In a few billion years, our central black hole could become several times larger than it is today. These comparisons also remind us of the sheer range of black hole environments in the universe. Sagittarius A-star is in a fairly calm spiral galaxy, surrounded by a mix of old stars, new stars, and moderate amounts of gas. TUN 618 sits in a far more active setting, with its quasar activity lighting up the cosmos. M87's black hole lies in a giant elliptical galaxy at the heart of a dense cluster, where galaxies frequently interact and collide. The size of a black hole is only part of its story. The neighborhood it lives in plays an enormous role in shaping its behavior. The surprisingly quiet giant. Black holes, by their nature, do not slow down with age. If matter falls toward them, they will devour it. The difference comes down to the amount of fuel available. At the present moment, Sagittarius A-star is surrounded by relatively little gas and dust compared to the central black holes of active galaxies. The material that does drift near tends to be scattered or heated in such a way that much of it never makes it all the way to the event horizon. Instead, it orbits for a while, loses some energy, and then is pushed back out into space by winds and turbulence. Only a small trickle of matter actually reaches the point of no return. Because the feeding rate is so low, Sagittarius A-star is faint, at least in black hole terms. Its emissions in radio, infrared, and X-ray wavelengths are minimal compared to its more voracious cousins. Quasars can be thousands of times brighter. If our black hole were to suddenly start consuming matter at the rate of an active quasar, the night sky would never be the same. A brilliant source would appear at the center of the Milky Way, visible even in daylight, outshining most of the stars. The idea is both fascinating and a little unsettling, as it would change the appearance of our galaxy dramatically. This subdued state is one reason it was so difficult to find in the first place. If Sagittarius A-star had been as active as the black holes in quasars, we might have detected its presence far earlier. The first X-ray and radio detections of the galactic center were faint enough that scientists needed years of patient observation to be sure of what they were seeing. Even at 26,000 light-years away, an actively feeding black hole would be an overwhelming beacon. The calm behavior of Sagittarius A-star tells astronomers some things about its surroundings. It suggests that the central region of our galaxy has gone through a relatively peaceful phase for millions of years. Other galaxies show evidence of violent outbursts from their central black holes, vast jets stretching thousands of light-years, bubbles of radio emission expanding into intergalactic space, and shockwaves heating surrounding gas. Our own galaxy shows only subtle hints of past activity, like the Fermi bubbles. If so, then our black hole is simply between meals right now, biding its time. Some scientists believe the quietness might be temporary. There are clouds of gas and streams of stars in the central region, and orbital mechanics ensures that from time to time, something will wander too close. When that happens, a sudden flare of activity could occur. In fact, astronomers have observed brief outbursts from Sagittarius A-star in recent decades. Sudden increases in X-ray and infrared brightness, lasting only hours before fading again. These could be caused by small amounts of material falling in, producing a momentary flicker before the calm returns. It's as if the giant occasionally stirs in its sleep. Many of the most active quasars host black holes billions of times more massive than the Sun. Their sheer size allows them to pull in much larger quantities of matter and to radiate far more energy. That size difference may partly explain the level of activity, since a smaller gravitational influence over Sagittarius A-star's surroundings might limit the amount of material it can capture. Still, size is not the only factor. There are known black holes with masses similar to or even smaller than Sagittarius A-star that are far more active. This reinforces the idea that the main difference is environment. If the Milky Way's central region had a denser supply of gas and dust, the story might be very different. In that alternate reality, Sagittarius A-star could blaze like the core of an active galaxy, influencing star formation across the Milky Way and reshaping the structure of our home. When astronomers point telescopes towards Sagittarius A-star, they can see details in the surrounding stars and gas that would be hidden if the black hole were more active. This has allowed incredibly precise tracking of stars in its vicinity. The calm environment also means that subtle changes in brightness can be studied in detail, giving insight into how black holes feed even at very low rates. Even in this subdued state, Sagittarius A-star emits radio waves. It also produces occasional X-ray and infrared flares, which, while faint compared to quasars, are still significant for understanding its behavior. These flares provide brief glimpses of the processes near the event horizon, showing how magnetic fields, turbulence, and hot plasma interact in extreme conditions. There is a certain mystery in watching something so massive, so fundamentally extreme in nature, and yet so restrained. It feels almost unnatural, a cosmic predator choosing not to hunt. Perhaps this is just a lull in its long history. Galaxies live for billions of years, and over such vast timescales, the feeding habits of their central black holes can shift dramatically. 1,000,000 years from now, Sagittarius A-star may be a roaring quasar. The quietness has a benefit for life in our galaxy. If Sagittarius A-star were highly active, the intense radiation from its core could potentially affect planets even thousands of light years away. In extreme cases, such radiation could strip away atmospheres or alter the chemistry of planetary surfaces. While Earth is far enough from the galactic center that such effects would be reduced, the overall habitability of the galaxy might be influenced by whether the central black hole is active or not. In that sense, the current calm might be a small factor in why life has been able to develop and thrive here. Is Sagittarius A-star a late bloomer? The future of Sagittarius A-star depends largely on whether it can find new food. Our galaxy is not empty, but the material near the black hole's immediate surroundings is relatively sparse. Most stars in the central region are in stable orbits that keep them from falling in. Gas clouds pass by, but not always close enough to be caught. However, galactic dynamics are unpredictable over long timescales. A close pass from a dense gas cloud or the disruption of a star could deliver a sudden meal. In fact, in recent years, astronomers tracked a large gas cloud known as G2 as it moved toward Sagittarius A-star. Many expected a dramatic flare-up when it got close, but surprisingly, the event was mild. G2 stretched and distorted, but much of it survived the encounter. This showed that not every close approach results in a feast for the black hole. Still, the possibility remains that a larger or denser cloud could one day trigger a feeding frenzy. If enough material falls in, Sagittarius A-star could become hundreds or even thousands of times brighter than it is now. The radiation would not reach Earth in a dangerous form, but it would change the appearance of the night sky. Observers would see the galactic center glowing far more intensely, possibly even visible to the naked eye under dark conditions. Another path to a more active future could come from galactic mergers. At some point, the Milky Way is expected to collide with Andromeda. When this happens billions of years from now, the stars themselves will mostly pass by each other without direct impact. But the gas and dust within both galaxies will be stirred up and funneled toward the centers. This could deliver a massive influx of fuel to Sagittarius A-star, causing it to flare into a true quasar phase. In such a state, it would unleash jets and winds that could reshape parts of the galaxy, blowing gas away and potentially halting star formation in the surrounding regions. Looking at other galaxies gives us a hint of what such a transformation could be like. In the distant universe, astronomers see supermassive black holes going through cycles of activity. Some are in the middle of an intense quasar stage, while others appear dormant. This suggests that black holes can have multiple active periods over their lifetimes. The timescales involved are so vast that human history is only a blink in the life of this object. It is possible that in 1,000,000 years, or 10 million, Sagittarius A-star will still be quiet. But perhaps in 25 million years, it will be in the middle of a feeding event, changing the appearance and behavior of our galaxy. There is even the possibility that it could consume an unusually large object, like a star cluster or a passing intermediate mass black hole, which could release energy on a scale far beyond what we see now. In cosmic terms, black holes are patient. They do not need to feed constantly, and they can go through long stretches without dramatic events. But when the right conditions arise, they can shift into a mode of intense activity almost instantly. Instruments like the Event Horizon Telescope, space-based X-ray observatories, and infrared telescopes are all helping to monitor the black hole's behavior. Small fluctuations in brightness can give clues about material moving inward. Even though a major outburst could be far in the future, the process leading up to it might be detectable years or centuries in advance. There is also a growing interest in looking for historical traces of its activity in other ways. Studying the orbits and composition of stars near the galactic center might reveal disturbances from past energetic events. Mapping the gas structures in the central regions can also show patterns shaped by older outflows. These are like the rings in a tree trunk, records of what the black hole has done before. If Sagittarius A-star does enter another active phase, it would be a rare chance to study a supermassive black hole's transformation in real time. Most of the quasars we see are so far away that their light comes from billions of years ago. To witness such a thing in our own galaxy would give scientists an unmatched opportunity to understand the mechanics of black hole feeding and feedback. It would also remind us that the Milky Way, though it feels stable, is still a dynamic and evolving system. The missing accretion ring. In the hearts of many galaxies, the presence of a glowing, furious ring of matter around a black hole is almost a given. These accretion disks are massive, swirling structures of gas, dust, and sometimes even stars, caught in a slow, spiraling death toward the event horizon. As they fall inward, friction and compression heat the material to incredible temperatures, causing them to radiate with the brightness of entire galaxies. This is why distant quasars can outshine everything around them, visible from billions of light-years away. But when astronomers looked toward Sagittarius A-star, they didn't see the blazing, unmistakable signature of such a disk. Instead, they found something faint. So faint that for decades it was uncertain whether it existed at all. At first, this absence puzzled scientists. After all, the central black hole of our galaxy was surrounded by countless stars, clouds of gas, and dust lanes that twisted like dark rivers through the galactic core. There seemed to be plenty of raw material for the black hole to consume. The answer, as it turns out, lies not only in the black hole itself, but in the delicate balance of its environment. One of the earliest hints came from radio and X-ray observations, which revealed that while there was indeed material moving toward the black hole, most of it never made it all the way in. Instead, much of the gas seemed to slow, heat up, and then be blown outward before crossing the event horizon. This led researchers to consider that Sagittarius A-star might be surrounded by what is called a radiatively inefficient accretion flow. In simpler terms, this means that the material falling toward the black hole isn't radiating much light because it's not dense or compact enough, and much of it escapes before the final plunge. Imagine trying to build a bonfire, but instead of tightly stacking the logs together, you scatter them loosely in a wide circle. The heat would still be there, but it would escape without creating the bright, intense flame you expect. This is similar to what's happening around Sagittarius A-star. The gas spiraling in is too spread out and too unstable to form a tightly packed, brilliant disk. Instead, much of it swirls in loosely and is eventually thrown back into space by powerful magnetic fields and turbulent flows. There's also the question of supply. For an accretion disk to blaze with the brightness seen in active black holes, it needs a constant and massive feed of matter. In galaxies hosting quasars, this feed often comes from intense bursts of star formation near the core, which drive vast amounts of gas toward the center. The Milky Way, however, is relatively calm at this stage in its life. While there are stars orbiting close to Sagittarius A-star, some even swinging within a hair's breadth on a cosmic scale, there is no massive influx of gas. In fact, some studies suggest that Sagittarius A-star might be in a long fasting period, where it is consuming only a trickle of matter compared to its past. Evidence from certain X-ray echoes bouncing off nearby gas clouds hints that just a few hundred years ago, our black hole may have been much brighter. If true, that means the ghostly disk we see today might be a remnant, slowly dissipating in the absence of a fresh supply of material. The search for the missing disk took on new urgency when the Event Horizon Telescope turned its gaze towards Sagittarius A-star. The EHT, a global network of radio telescopes working together to act as a planet-sized observatory, was able to resolve the faint halo of emission around the black hole. What they saw was not a flat, bright disk like the one imaged around the black hole in M87, but a more irregular and patchy structure. This reinforced the idea that Sagittarius A-star's accretion flow is thin, hot, and chaotic, producing far less radiation than one might expect. But this doesn't mean the disk is unimportant. Even a faint accretion flow can provide clues about the behavior of matter in extreme gravity. The weak emission we do detect gives scientists a way to measure the temperature, density, and motion of the gas. These measurements suggest that the plasma near Sagittarius A-star is incredibly hot, tens of millions of degrees, yet still too tenuous to produce the blinding light of a more active system. Another piece of the puzzle comes from the orbits of S-stars, which pass close enough to Sagittarius A-star to potentially shed material into its gravitational pull. Yet, the accretion disk remains faint. This has led to speculation that the black hole may be very selective about what it consumes. Magnetic fields and turbulent flows in the surrounding plasma could be acting like a cosmic shield, deflecting much of the infalling gas before it can reach the inner disk. Still, the mystery remains. Was the ghostly disk always like this, or is it the result of a recent drop in feeding? Will it flare to life again if a large cloud of gas or a star drifts too close? In 2014, G2 passed with little more than a murmur. This may have been because G2 was a star cloaked in dust rather than a free-floating gas cloud, which would explain why so little material ended up in the disk. What is certain is that the missing accretion disk is not truly missing. It's simply faint, fragmented, and underfed. For now, we live alongside a sleeping giant whose hunger is subdued. The flares we can't predict. Every so often, the calm, dim glow around Sagittarius A-star is broken by a sudden burst of light that seems to come from nowhere. These flashes, or flares as astronomers call them, appear without warning. One moment, the region near the black hole is quiet and subdued. The next, it's as if someone has turned up the cosmic brightness knob for a brief moment before letting it fade again. These flares can be dramatic. Sometimes the brightness can increase dozens of times above its usual level, only to return to normal within a couple of hours. They don't happen on a fixed schedule. They aren't tied to anything obvious that we can see in advance. And because Sagittarius A-star is hidden behind thick clouds of gas and dust, the suddenness of these events makes them all the more intriguing. When a flare happens, scientists drop whatever else they're doing and point every available telescope at it, trying to gather every scrap of information before it fades. The first time astronomers noticed these flares, they were surprised by both their intensity and speed. The timing suggested that the flares were coming from very close to the event horizon. The rapid rise and fall in brightness hinted that the source was compact, no larger than the distance light could travel in a few minutes. This was a strong clue that something near the heart of the black hole's immediate surroundings was responsible. But what exactly? One possible explanation is that these flares are caused by clumps of gas falling inward. In normal conditions, the matter around Sagittarius A-star is too thin and sparse to produce much light. But occasionally, a denser pocket of material, maybe from a nearby star shedding its outer layers or a cloud of dust drifting too close, could find itself caught in the black hole's pull. As it spirals inward, the gas heats up to millions of degrees, releasing a burst of energy before vanishing into the black hole. This would create a sudden flare. Another possibility involves magnetic fields. Black holes can twist and tangle magnetic field lines in their surroundings, storing enormous amounts of energy. If these magnetic fields suddenly reconnect, a process similar to what happens in solar flares on the Sun, they could unleash a rapid burst of radiation. In this view, the flare is not just a side effect of matter falling in, but a direct release of pent-up magnetic energy. This could explain why some flares appear without any sign of new material being swallowed. A third idea is that the flares are caused by stars or smaller black holes passing dangerously close to Sagittarius A-star. In such encounters, tidal forces could rip apart chunks of material, sending them spiraling into the black hole and producing an intense flash. While this is less likely to happen frequently, it can't be ruled out. After all, the galactic center is a crowded place. Astronomers can't schedule an observation and expect a flare to appear. It's a waiting game. Teams sometimes monitor Sagittarius A-star for weeks at a time, hoping to catch even one brightening event. And when they do, they must react quickly, coordinating with telescopes on the ground and in space to record the flare across as many wavelengths of light as possible, from radio waves to X-rays. The goal is to piece together a complete picture of what happens during these brief episodes. Interestingly, the flares tend to occur more often in X-ray and infrared light than in visible light. This fits with the idea that they are caused by very hot material close to the black hole, since such high energy environments naturally emit more in these parts of the spectrum. But even with this knowledge, there's no simple pattern. Some flares are stronger in X-rays, others in infrared. Some last only a few minutes, while others linger for hours. The variety suggests that more than one process might be at work. A particularly famous flare happened in 2019, when Sagittarius A-star became brighter than ever recorded before, more than twice its previous maximum. The intensity shocked scientists, and for a brief moment they wondered if something major had happened, like a star being torn apart. But follow-up observations suggested it was likely a massive clump of gas falling in, perhaps related to G2, which had been drifting near the black hole for years by this point. This event showed just how dramatic Sagittarius A-star can be when it decides to stir from its usual slumber. If such bursts can happen today, in its relatively quiet state, what might they have looked like in the past when the black hole was more active? Evidence from X-ray echoes in nearby clouds suggests that hundreds of years ago, Sagittarius A-star may have been hundreds of thousands of times more luminous than it is now. In that light, today's flares might be small-scale reminders of a much wilder, more energetic past. For now, the bursts are brief and isolated, but if the black hole's surroundings change, it could feed much more vigorously. The occasional flare might be the cosmic equivalent of a stomach growl before a real feast begins. Scientists hope that by studying more flares in detail, they can narrow down the causes and understand the physics at play. The coming years should bring major improvements in this field. Instruments like the EHT are now being used to watch Sagittarius A-star directly. Combined with space-based X-ray and infrared telescopes, these observations could finally allow astronomers to see a flare as it forms, track its evolution in real time, and match it to specific physical processes. Magnetic mayhem, twisting fields near the event horizon. Close to the edge of Sagittarius A-star, the rules of the universe start to feel less like constants and more like shifting patterns. Here, gravity is not the only dominant force. Invisible but incredibly powerful magnetic fields twist and writhe like living things. They thread through the surrounding space, wrapping around arcs of plasma, guiding the flow of charged particles, and sometimes, perhaps, choking it off entirely. For a long time, astronomers assumed that magnetism near a black hole was just a byproduct, a background feature of the swirling gas. But now, it's becoming clear that these tangled fields might be at the heart of the black hole's strange behavior. The idea of magnetic fields near a black hole might sound almost contradictory. After all, a black hole swallows everything that comes too close. How could anything survive there, let alone a structure as delicate as a magnetic field? The key is that the black hole itself is not generating them in the same way Earth's molten core produces our own magnetic field. Instead, the fields come from the plasma surrounding the black hole. As this gas moves, it drags its own magnetic field lines with it, stretching and twisting them into complex knots. Sagittarius A-star's magnetic fields are not neat, stable loops like those around our planet. They are chaotic, constantly shifting as the gas around them flows, collides, and heats up. The EHT's polarized light data has given astronomers the first real look at these magnetic structures, revealing spiraling patterns in the faint glow around the black hole. The patterns tell us that the fields are strong enough to shape the motion of matter, not just passively drift through it. In a way, magnetism is competing with gravity here. Gravity wants to pull everything inward, dragging it toward the event horizon. Magnetic fields can push back, especially when they become tightly wound. They can act like barriers, holding material in place or redirecting it along certain paths. This could be part of the reason Sagittarius A-star is so quiet. If the magnetic fields are organized in a certain way, they might prevent gas from plunging in all at once. Instead, the material trickles in slowly, producing only weak emission. But these same magnetic fields can also store enormous amounts of energy. When they snap or realign, they can unleash bursts of radiation. A sudden reconnection event near the event horizon could accelerate particles to extreme speeds, causing them to emit X-rays and infrared light in short, sharp flashes. The flare fades as the energy dissipates, leaving the black hole dim again until the next event. There's also a mystery about how these magnetic fields are arranged in 3 dimensions. Some models suggest they could form large-scale loops extending far from the black hole, threading through the surrounding region known as the accretion flow. Others propose a much more tangled mess, where lines are constantly breaking and reforming. Observations so far hint at some degree of order close to the black hole, but chaos farther out. This could mean that Sagittarius A-star's environment is in a delicate balance, stable enough to avoid constant eruptions, but unstable enough to produce occasional bursts of activity. In other systems, strong fields can launch powerful jets, beams of plasma shooting out at near light speeds. Sagittarius A-star doesn't have obvious large-scale jets, but there are hints of smaller, weaker outflows. If magnetism is involved, these outflows might be acting as a kind of pressure valve, releasing energy and gas that would otherwise feed the black hole more directly. This could be another reason it stays so faint most of the time. Near the event horizon, conditions are so extreme that the usual rules for how plasma behaves begin to break down. Magnetic fields can influence particles in ways we can't fully model yet, especially when relativistic effects are involved. Charged particles spiraling along field lines near light speed can produce polarized radiation, and by studying that polarization, astronomers can decode the field's shape and strength. The patterns in this light are some of the few direct clues we have about what's happening in a region we can never visit. The magnetism near Sagittarius A-star is part of a larger story about the interplay of forces in one of the universe's most extreme environments. Gravity may dominate the structure, but magnetism adds a layer of complexity that changes how the black hole feeds, flares, and interacts. It's an invisible architecture shaping a cosmic environment just beyond the point of no return. The more we understand about these twisting fields, the closer we get to understanding the hidden engines that power black holes across the universe. The Schwarzschild radius up close. The Schwarzschild radius is one of the simplest ways to describe a black hole. It is the size of the event horizon. If you cross this line, you are gone from the visible universe forever. The term comes from the German physicist Karl Schwarzschild, who in 1916 was the first to find a mathematical solution to Einstein's new theory of general relativity that described such an object. His equations told us that if you compress enough mass into a small enough space, the pull of gravity becomes absolute at a certain radius. That radius depends only on the object's mass, and for black holes, it is all that's left to define their size. For Sagittarius A-star, the mass is about 8.54 times 10 to the power of 36 kilograms. When you plug that into the Schwarzschild formula, you get a radius of roughly 12 million kilometers, or about 7.4 million miles. That sounds huge, and in human terms it is, but in cosmic terms it's surprisingly small. It's just over 17 times the diameter of the Sun, all packed into an invisible sphere at the heart of the Milky Way. Everything inside that sphere is cut off from the rest of the universe. The black hole itself is not a physical ball. The event horizon is not a solid surface you could touch. It's simply the threshold where space and time bend so steeply inward that no outward path exists. From far away, the Schwarzschild radius is a purely mathematical line. You could orbit near it, circle around it, even hover just outside it if you had some impossible way to counteract gravity. But get closer and the landscape changes. Space itself is falling inward, pulled faster and faster as it approaches the event horizon. The closer you are, the more extreme time dilation becomes. From your perspective, everything would seem normal. From the outside, you would appear to slow down, your light shifting to red, fading, and eventually disappearing entirely before you ever seem to cross the line. The Schwarzschild radius marks the point where the inward pull becomes infinite from the outside universe's perspective. Sagittarius A-star's Schwarzschild radius has been the focus of intense study in recent years, especially with the EHT. The EHT image of Sagittarius A-star shows a glowing ring of radio light around a dark center. That dark center was not the black hole itself, but its shadow, a slightly larger silhouette caused by light being bent and swallowed near the event horizon. The actual Schwarzschild radius lies just inside that shadow's edge. In this sense, we've now seen the boundary, even if not in a direct visual photograph. Because it's so far away, the whole thing appears smaller in the sky than a donut on the moon would look to someone standing on Earth. That's why imaging it took years of coordination, enormous computing power, and the precision of atomic clocks. Beyond the Schwarzschild radius lies the region we cannot observe directly. According to general relativity, once you pass the event horizon, you are inevitably drawn toward the singularity at the center. The singularity is a point of infinite density, where the known laws of physics break down. We do not know what really happens there. Some theories suggest it might be a tiny, infinitely curved region of space-time. Others propose that quantum effects could smear it out or replace it entirely with something new, perhaps a Planck star or a bridge to another universe. But as far as our instruments are concerned, it is forever hidden. The Schwarzschild radius is not just a limit for light, it's a limit for cause and effect. No signal from inside can ever influence the outside. That means the inner workings of a black hole are cut off from the rest of the cosmos in a very fundamental way. This is why so much of black hole science has to be done indirectly. We measure the orbits of nearby stars, watch how hot gas behaves, or detect the flickers of light caused by magnetic or gravitational turbulence just outside the event horizon. Sagittarius A-star is not unique in having a Schwarzschild radius of this size. Any object of 4 million solar masses would have the same value. What makes it unique is its position in our galaxy, and the fact that we can study it in detail compared to others. Black holes with billions of solar masses have much larger event horizons, sometimes bigger than our entire solar system. In contrast, a stellar mass black hole might have a Schwarzschild radius of only a few kilometers. This is why scientists often describe black holes in terms of their mass rather than their physical size. It's mass that determines the radius in the first place. Once you know a black hole's mass, you know its Schwarzschild radius. You also know something about the speed needed to escape from just outside it. The escape velocity equals the speed of light. That's the defining trait. For any other object, planets, stars, even neutron stars, escape velocity is lower, which means light can still get out. But at the Schwarzschild radius, the pull is too strong for even photons. Near Sagittarius A-star's Schwarzschild radius, conditions are violent even in its current quiet state. Magnetic fields twist and snap, charged particles spiral at near-light speed, and space-time itself is dragged around by the spinning black hole. Even though Sagittarius A-star is relatively calm now, the zone just outside the horizon is still an extreme laboratory for physics. It's here that matter in the accretion flow heats to millions of degrees and emits the radio waves that the EHT detected. It's here that flares of X-rays and infrared light sometimes burst out when clumps of gas plunge inward. From radio dishes to space telescopes, a timeline of discovery. In the mid-20th century, the center of the Milky Way was still mostly a mystery. Throughout the 1980s, radio astronomy remained the primary tool for studying this strange source. Observations with the VLA in New Mexico sharpened the view, showing that Sagittarius A-star was not only compact but also variable. Its radio output would rise and fall over time. The next leap forward came from pushing interferometry to a much greater scale. In the 1990s, scientists began linking radio dishes spread across the globe in a technique called Very Long Baseline Interferometry, or VLBI. This allowed them to create a virtual telescope the size of Earth, dramatically improving resolution. By combining data from observatories thousands of kilometers apart, they could begin to measure Sagittarius A-star's apparent size, just tens of micro-arcseconds across. In the 1990s, infrared astronomy came into its own thanks to new detectors and adaptive optic systems that could counteract the blurring effects of Earth's atmosphere. Over years of careful measurement, two separate teams mapped how stars moved in tight, fast orbits around the invisible point. NASA's Chandra X-ray Observatory, launched in 1999, revealed that Sagittarius A-star occasionally emits bright flares in X-rays, showing it was not entirely dormant. The Spitzer Space Telescope mapped the crowded star fields and warm dust near the center with unprecedented clarity. By moving above Earth's atmosphere, these observatories bypassed distortions and absorbed wavelengths, allowing scientists to gather cleaner, more detailed data. In the 2000s, sub-millimeter astronomy became another major tool. This part of the spectrum, between infrared and radio, is especially good for studying cold dust and the emission from matter close to black holes. The sub-millimeter array in Hawaii, and later the Atacama Large Millimeter Sub-Millimeter Array, or ALMA in Chile, gave researchers a sharper look at the surroundings of Sagittarius A-star. These arrays, with their high-altitude locations and wide baselines, could detect fine details in the faint emissions from the galactic center. The ultimate imaging challenge, however, was to see the shadow of the black hole itself, a feat only possible by pushing VLBI to the extreme. This is where the EHT came in. Starting in the 2010s, the EHT linked together a network of radio observatories scattered across the globe, including ALMA, the South Pole Telescope, and others in North America, Europe, and Asia. Observations were conducted at 1.3 millimeters, a wavelength that can pass through much of the galactic dust while offering incredibly high resolution. In 2017, the EHT turned its full attention to Sagittarius A-star. Processing the data took years because the black hole's appearance changes rapidly. Material whirling close to the event horizon moves at near light speed, causing the brightness pattern to shift in minutes. Combining data from multiple sites into a coherent picture required complex algorithms and careful averaging over time. Finally, in 2022, the EHT team released the first ever image of Sagittarius A-star, a blurry but unmistakable ring of light surrounding a dark central shadow, exactly what theory predicted for a black hole of its mass. Each step reflects both technological progress and the persistence of the scientists involved. From the first crude radio detections to a direct image of the event horizon's silhouette, the journey spanned decades and required innovations in instrumentation, computing, and observation techniques. New instruments, such as the James Webb Space Telescope, are probing the galactic center with unmatched sensitivity in the infrared, while upgrades to the EHT promise even sharper images in the years ahead. The discovery of Sagittarius A-star has been a gradual unveiling, each generation of instruments peeling back another layer of mystery. And with every improvement in our tools, we see a living, changing part of the Milky Way story, how gravity lens helped focus our view. Light does not simply travel in straight lines through an empty stage. Instead, the very fabric of space can bend it, twist it, and even focus it like a giant lens. This bending of light, known as gravitational lensing, is one of the most extraordinary tools that nature itself has provided to astronomers. For researchers studying Sagittarius A-star, this natural phenomenon has, in certain cases, given us sharper glimpses into the dark heart of our galaxy. Imagine placing a heavy ball on a rubber sheet. The ball will sink in, creating a depression. Now, if you roll a marble across the sheet, it will curve around the dip rather than moving in a straight path. In space, massive objects like stars or black holes play the role of the heavy ball, and light is the marble. The sheet is the invisible fabric of space-time. When light from a distant object passes near something massive, the gravity of that object warps space-time and changes the light's path. To us, observing from afar, it can look as if the light has been bent or focused. When applied to Sagittarius A-star, gravitational lensing becomes more than just a clever trick of physics. The galactic center is packed with stars, clouds of gas, and other dense objects. Sometimes, these objects pass between us and Sagittarius A-star, briefly bending the light in ways that allow astronomers to gather more detail than they could otherwise. This can be especially valuable because our line of sight to the galactic center is normally clouded by dust. Lensing can act like a cosmic cleaning of the lens, allowing more clarity in moments when it aligns just right. The effect can occur on different scales. In some cases, individual stars orbiting close to Sagittarius A-star can act as tiny lenses, magnifying background objects. This microlensing can help researchers detect faint objects that would otherwise be invisible. In other cases, entire regions of dense gas or clusters of stars can create a larger lensing effect, warping the light from even more distant sources. By studying these distortions, scientists can reconstruct the paths of light and learn more about what lies in the center of the Milky Way. Not only can intervening objects lens the light from the galactic center, but Sagittarius A-star itself, with its immense gravity, can bend light from background stars. This bending can cause multiple images of the same star to appear, or stretch the star's light into arcs. By carefully measuring these distortions, astronomers can get extremely precise readings of the black hole's mass and even hints about the distribution of matter near the event horizon. However, capturing these events is not easy. Gravitational lensing requires near-perfect alignment between the observer, the lensing object, and the background source. These alignments are rare and often short-lived, especially in the dynamic environment around the galactic center. Observatories have to be ready to monitor this region constantly, watching for subtle shifts in brightness or position that signal a lensing event. This is where networks of telescopes spread across the globe become critical. They can watch the same spot from different locations, ensuring nothing is missed. The first hints of gravitational lensing effects near Sagittarius A-star were not immediately recognized for what they were. Early radio astronomers sometimes noticed odd brightening of background sources, but the tools to confirm lensing were not yet refined. As technology improved, and as the theories of how lensing works became more widely accepted, these earlier data points gained new meaning. Now researchers can not only identify lensing events, but also predict them in some cases, thanks to detailed tracking of star movements. Even with our most advanced telescopes, the region just outside the event horizon is tiny from our perspective. Lensing allows us to peek into this zone with a boost in resolution, offering insights into the shape of the accretion flow, the distribution of magnetic fields, or the dynamics of orbiting material. These details are essential for testing our models of black hole behavior. Another subtle benefit of gravitational lensing is that it can act as a natural amplifier for faint bursts of radiation. Sometimes, a lensing effect can make a flare stand out more clearly against the background, allowing researchers to study its timing, duration, and intensity with better accuracy. In some rare alignments, the flare's light might even take two different paths around the black hole before reaching us, creating a delayed echo that can be measured. While gravitational lensing is often described in terms of its visual impact, it also plays a role in other wavelengths. Radio waves, Infrared light and even high-energy X-rays can be bent by gravity in exactly the same way as visible light. This means that the benefits of lensing apply to the full range of observations used to study Sagittarius A-star. Radio arrays, infrared observatories, and X-ray satellites have all recorded data that hint at or directly show lensing effects near the galactic center. If Sagittarius A-star ever becomes brighter and more violent, gravitational lensing could magnify the effects of its outbursts. This might make the black hole's activity visible to observers much farther away, potentially even to civilizations in distant galaxies. In this way, lensing does not just aid our study of the black hole, it could also help spread its presence across the cosmos. While it is already proving useful, many researchers believe we have only scratched the surface of what it can reveal. With the next generation of instruments and observatories, including instruments capable of even finer resolution and sensitivity, the coming decades could see gravitational lensing used as a standard tool for probing the deepest secrets of our galaxy's central black hole. Adaptive optics and the warped view of the center. The light from stars near Sagittarius A-star has to pass through the thick layers of Earth's atmosphere before reaching detectors. This atmosphere, while essential for life, is far from friendly to delicate astronomical measurements. Air currents move unpredictably. Pockets of warmer and cooler air bend and twist the incoming starlight in different ways. This bending changes constantly, and it causes stars to appear as though they are shimmering or wobbling, an effect anyone can see by looking up at twinkling stars on a clear night. For astronomers trying to track the fine details of stars orbiting close to the black hole, that twinkling is not charming. It is a serious problem. For a long time, this distortion meant that even the most powerful ground-based telescopes could not produce perfectly sharp images of the galactic center. The solution came from a breakthrough in technology called adaptive optics. Instead of simply trying to design better lenses or mirrors to work around the problem, adaptive optics attacked the issue at its source, the moving atmosphere. The basic idea is that if the atmosphere bends starlight, then a telescope could use a flexible mirror that bends in the opposite way, undoing the distortion in real time. To figure out exactly how to bend that mirror, astronomers first need to measure the distortion. In practice, they do this by aiming at a bright reference point in the sky. Sometimes this is a real star, but often astronomers create an artificial one by shining a powerful laser into the upper atmosphere. The laser excites sodium atoms about 90 kilometers above Earth, making them glow and form a bright point of light. By analyzing how this artificial star's light gets warped on its way down, computers can instantly calculate the changes needed for the mirror. The mirror surface shifts and flexes hundreds of times per second, counteracting the effects of the atmosphere. When adaptive optics first began to be used for studying Sagittarius A-star, it was nothing short of a revolution. Stars that once looked like fuzzy patches suddenly came into sharp focus. The true structure of the central star cluster emerged in unprecedented detail. Astronomers could now track the movement of individual stars as they swung around the invisible mass at the center. Adaptive optics also allowed researchers to study the light from these stars in finer detail. Spectroscopic measurements, splitting the light into its component colors, became more precise. This opened the door to learning about the star's speeds, chemical compositions, and interactions with the extreme environment near the black hole. The difference between pre-adaptive optics and post-adaptive optics data was like switching from a cloudy lens to high-definition vision. But even with this technology, the galactic center is not an easy place to observe. Dust clouds still block much of the visible light, so astronomers often work in the infrared range. Adaptive optics works in infrared too, and that combination, infrared sensitivity and real-time atmospheric correction, has been the key to unlocking many discoveries about Sagittarius A-star. Without it, some of the most important measurements, such as the gravitational redshift of light from S2 or the precise mapping of stellar orbits, would have been impossible. The Earth's atmosphere is constantly changing, with turbulent patterns evolving over milliseconds. The system's computers must detect, calculate, and correct for these changes in the same time frame. The mirrors used are highly specialized, often made of thin, flexible materials like glass or even metal coated with reflective surfaces. Tiny actuators push and pull on different points of the mirror to create just the right shape. The precision involved is almost hard to grasp. Movements are often smaller than the width of a human hair, yet they have a profound impact on the clarity of the image. Over time, the technique has been refined. Early systems could correct for general distortions, but struggled with the finest details. Modern systems, installed on some of the world's largest observatories, can account for different layers of the atmosphere separately. This is important because not all turbulence happens at the same height. Wind patterns in the lower atmosphere, jet streams at high altitude, and localized heat rising from the ground all play different roles in bending light. Multi-conjugate adaptive optics, as it's called, uses several reference points and multiple deformable mirrors to address these layers independently. The result is a broader and more uniform correction, which is especially useful for wide-field imaging of the galactic center. For Sagittarius A-star, this has meant that astronomers can now do more than track stars. They can look for subtle changes in brightness or position that might hint at unseen companions, faint clouds of gas, or the motion of hotspots near the black hole's event horizon. Adaptive optics has even been combined with interferometry. This approach pushes resolution even further, allowing scientists to peer into regions once thought completely unreachable from the ground. The success of adaptive optics has not gone unnoticed. It is now considered a standard tool for cutting-edge astronomy, and the lessons learned from studying Sagittarius A-star have influenced its development for other purposes. Observations of distant galaxies, exoplanets, and even asteroids have all benefited from this technology. But in the case of the Milky Way's black hole, the impact has been especially profound. It has turned what was once a turbulent and shifting image into a clear, steady view, revealing a dynamic and crowded region where gravity reigns supreme. And while adaptive optics has transformed our view from Earth, it works best when paired with other methods. Space telescopes, free from atmospheric distortion, still provide unmatched stability, but they cannot have mirrors as large as some ground-based observatories. Combining the size and power of these giant Earth-based telescopes with the atmospheric correction of adaptive optics has created a balance. We can now study Sagittarius A-star with a level of detail that would have been unthinkable just a few decades ago. The road to the first black hole photo. In 2019, the world saw a picture of M87 star. M87 star has a mass about 6.5 billion times that of our Sun, which makes its event horizon huge in comparison. Its size was one of the reasons scientists chose to target it before Sagittarius A-star. A bigger black hole produces a larger shadow against the surrounding light, making it easier to image despite its incredible distance. The larger mass also means that matter orbiting near the event horizon moves more slowly, so changes in brightness happen over hours or days rather than minutes, as with Sagittarius A-star. This gave astronomers more time to gather the data they needed without the image becoming too blurred by rapid changes. No single telescope on Earth is big enough to see the event horizon of a black hole. To get the necessary resolution, the telescope would need to be about the size of our planet. Since that's obviously not possible as a single instrument, scientists linked radio telescopes across the globe to form the EHT. By coordinating these facilities to observe M87 star at the same time, and precisely combining the data from each, scientists could effectively create an Earth-sized telescope in terms of resolution. The precision required for this was mind-boggling, down to syncing atomic clocks so accurate they would lose less than a second over millions of years. Each observatory collected vast amounts of data, which couldn't simply be sent over the internet because the volume was so large. Instead, the data had to be physically stored on special hard drives and flown to a central location for processing. The observation campaign for M87 star took place in April 2017. For several nights, every participating telescope pointed toward the galaxy, recording high-frequency radio waves emitted by matter swirling near the event horizon. These observations took place at a wavelength of 1.3 millimeters. Weather had to be perfect at every site involved because poor conditions at even one telescope could ruin the data. After the observing run, the real work began. The petabytes of raw data were shipped to powerful computing centers, where teams of scientists began the process of correlating and calibrating the signals from all the telescopes. This step was essential because each telescope recorded slightly different information, and the timestamps had to be matched perfectly to reconstruct the interference patterns. These patterns were then used to generate an image, but even that was not as straightforward as taking a photograph. There were gaps in the coverage of the virtual Earth-sized telescope, so algorithms had to fill in missing details. To avoid bias, the imaging process was split among multiple independent teams, each working without knowledge of the other's results. When the images were finally compared, they matched closely. On April 10, 2019, the EHT team revealed the image to the world, a blurry orange donut against a black background, representing the light from hot matter bending around the event horizon of M87 star. It was a visual confirmation of general relativity in one of the most extreme environments in the universe. The size and shape of the shadow matched the predictions almost perfectly. The photo instantly became one of the most iconic images in science. It proved that millimeter wavelength interferometry could image black holes, something many thought might be impossible. It also opened the door to eventually imaging Sagittarius A-star. While our own black hole is closer and appears larger in the sky than M87 star, it is also far more challenging to photograph. The success of M87 star was a critical test run. It allowed scientists to refine their techniques, improve their algorithms, and gain the confidence needed to attempt the more difficult target in our own galaxy. It also taught them about the behavior of black holes in general. The bright ring seen in the image was caused by synchrotron radiation from electrons spiraling along magnetic fields. The asymmetry in the brightness of the ring showed that the matter around the black hole was moving at near light speeds, with one side boosted in brightness due to relativistic effects. Since that first image, the EHT has expanded, adding more telescopes to increase its resolution and sensitivity. It has also started working at multiple wavelengths to probe different aspects of black holes. The lessons from M87 star continue to influence how scientists think about black hole physics as a whole. The road to that first photo was a testament to global cooperation in science. Teams from different countries with different expertise and languages worked together toward a single goal: to see the unseeable. It is easy to forget how much of this was uncertain in the beginning. Before the EHT, no one knew if the turbulent gas around a black hole would even produce a clean enough shadow to detect. The fact that the image turned out so clear and so close to theoretical predictions gave researchers more confidence in the models they used to study the cosmos. It also inspired a new wave of scientific projects aimed at pushing the limits of imaging technology even further. Already, there are proposals for next-generation EHT arrays that would include telescopes in space, providing even longer baselines and sharper resolution. One day, it might even be possible to make time-lapse movies of matter falling into a black hole, showing in real time the dance of energy and gravity at the very edge of physics. The M87 star image brought black holes into the public imagination in a new way. For decades, they had been the stuff of chalkboard equations and computer simulations. Now, for the first time, people could look at an actual image and know they were seeing the edge of a place where the known laws of the universe break down. Why imaging Sagittarius A-star was 10 times harder. Sagittarius A-star's smaller size means that the light, or more accurately, the radio waves, from its surrounding material has a much smaller target to trace. From Earth, Sagittarius A-star appears to be about the size of a donut sitting on the moon. It is also more lively than M87 star. While M87 star changes over timescales of days to weeks, Sagittarius A-star changes on the order of minutes to hours. The gas swirling around it is so close to the black hole that it orbits at incredible speeds, sometimes circling in just a few minutes. This means that by the time astronomers try to stitch together an image, the target they're looking at has already changed shape. For M87 star, the glow of the disk stays relatively stable during the observing window, making it easier to produce a sharp image. For Sagittarius A-star, it's like trying to take a long exposure photograph of a candle flame in the wind. The flickering keeps smearing the result. The atmosphere between Earth and Sagittarius A-star adds yet another layer of complexity. M87 star lies far outside our galaxy, so its radio waves travel mostly through intergalactic space before reaching us. Sagittarius A-star, on the other hand, sits inside the crowded center of the Milky Way. Dust particles scatter the radio waves, blurring and distorting the view. Correcting for that blurring requires heavy data processing, and even then, some fine detail is inevitably lost. For M87 star, the observing campaign could be spread out without too much concern. For Sagittarius A-star, all participating telescopes had to be synchronized with extreme precision so that they captured the same constantly changing target at the exact same moments. Even a short delay could mean that the data from one telescope would be looking at a different version of the black hole than the others, ruining the image. Weather became a much more serious problem for this reason. The EHT network includes observatories from Chile to Hawaii to the South Pole. For Sagittarius A-star, all these sites needed clear skies at the same time, over several days, and during the same short observing window when the black hole was in the right position in the sky. A storm in Chile or clouds in Hawaii could throw off the entire schedule. Coordinating this was like planning a global concert where every musician had to play the exact same note at the exact same instant, but where each stage was on a different continent and the instruments were extremely sensitive to the weather. The imaging process itself also had to be rethought. The rapid variability of Sagittarius A-star meant that the traditional approach, treating the black hole as a static object, wouldn't work. Scientists had to develop new algorithms to handle a target that was morphing while they were trying to observe it. Instead of a single stable image, they ended up generating thousands of possible images and looking for patterns that remained consistent across them. This was the only way to be sure that what they were seeing was real and not an artifact of the changes happening during observation. M87 star is surrounded by a steady inflow of gas that produces a bright glowing ring. Sagittarius A-star's accretion is much weaker, meaning less radiation is emitted from its surroundings. This low brightness makes it harder to get a strong, clean signal. It's a bit like trying to photograph a faint candle in daylight compared to photographing a campfire at night. The campfire, like M87 star, naturally stands out. The candle, like Sagittarius A-star, gets lost in the noise unless the photographer takes extra care. At shorter radio wavelengths, the scattering from the galactic plane is worse, making the image blurrier. At longer wavelengths, the scattering is less of an issue, but the resolution decreases and the black hole's features become harder to distinguish. Finding the sweet spot in wavelength choice was a balancing act between resolution, clarity, and brightness. Stars, clouds of gas, and other radio sources all lie in the same direction, and their signals can overlap. Separating these signals is possible, but only with careful filtering and cross-checking. This required months of analysis after the observations were completed, as scientists painstakingly removed unwanted background signals from the data. By the time the final image of Sagittarius A-star was ready, the scientists had processed petabytes of raw data, run thousands of simulations, and tested countless variations of their imaging algorithms. Every step was checked and rechecked to make sure the image truly reflected the black hole's structure and wasn't a byproduct of the methods used. When the picture was finally released in 2022, it showed the now familiar blurry ring remarkably similar in shape to M87, stars, but fuzzier and more variable. Behind that fuzziness lay years of work, much of it tackling problems that had no precedent. It's easy to think of Sagittarius A-star as a natural next step after M87 star, but in many ways it was a leap. All its issues combined to make it one of the more stubborn targets in modern astronomy. The success of its image was a demonstration of how creative problem-solving, coordination, and a willingness to rethink established methods can overcome challenges that at first seem insurmountable. What the photo didn't tell us. When the image of Sagittarius A-star was released to the public, it was celebrated as one of the most significant scientific achievements of the decade. But for scientists, the photo was not the end of the journey. In many ways, it was just the beginning. The picture confirmed certain things we expected, but it also left us staring at a long list of questions that remain unanswered. The first and most obvious gap in our understanding comes from the fact that the image does not directly tell us how fast Sagittarius A-star is spinning. Black holes can have different rotation rates, from no spin at all to the maximum allowed by physics. The spin affects the shape of the event horizon, the way matter orbits the black hole, and the power of any jets or energetic outflows. But determining that spin from a blurry, averaged image is far from simple. For M87 star, scientists had a better chance of narrowing down the spin because the black hole changes much more slowly. Sagittarius A-star's bright spots in the accretion flow are constantly moving and reshaping the pattern of light. When the EHT team compiled their final image, it was an average of many different moments. This made it harder to pick out stable features that might reveal the rotation. The spin might still be hiding in the data, waiting for a different kind of analysis, but it's not something the first image could tell us outright. The second major unknown is the orientation of Sagittarius A-star. A black hole doesn't have a top or bottom in the way a planet does, but it does have an axis of rotation, like a giant spinning sphere. Knowing the tilt of that axis relative to Earth is important for understanding how matter falls in, how energy might be released, and how it interacts with the rest of the galaxy. For M87 star, this was easier to estimate because the black hole produces a visible jet which gives a clear directional clue. Sagittarius A-star doesn't have a prominent jet we can see. It might have smaller outflows, but they are weak and hard to detect through the crowded, dusty center of the galaxy. Without that guiding line, the orientation is still uncertain. The EHT image was taken in a way that didn't directly capture the polarization of light, which is one of the best indicators of magnetic field structure. Follow-up observations are beginning to focus on polarization. But for now, the exact shape and strength of the magnetic fields around Sagittarius A-star remain mysterious. The image we saw was an average, but what does Sagittarius A-star look like at any given moment? If we could take rapid snapshots instead of long averages, we might see hotspots orbiting close to the event horizon, patterns in the flow of gas, or flares bursting into view. These could tell us much more about the black hole's behavior. But to get a clear picture at such fine resolution, telescopes have to collect data over many hours. The image also doesn't tell us the full story of how much matter is actually falling into Sagittarius A-star. It doesn't reveal the long-term feeding habits of this black hole. Even the shadow raises questions. General relativity predicts a certain size for the shadow based on the black hole's mass. The image of Sagittarius A-star matches that prediction fairly well, but the margin of error is still large enough that alternative theories of gravity are not entirely ruled out. A more precise image might one day tighten those limits, telling us if space and time truly behave exactly as general relativity describes. The light we detect from Sagittarius A-star at radio wavelengths has already been filtered and scattered by the turbulent clouds along the way. Astronomers correct for this, but there's always a chance that some subtle features are blurred beyond recovery. This is part of why improving resolution and working at multiple wavelengths is so important for the future. These unanswered questions are central to understanding what Sagittarius A-star actually is and how it behaves. The photo gave us a face for the black hole, but it didn't give us its full identity. More observing runs with the EHAT are being planned, this time including more telescopes to improve image quality. There's also an effort to capture polarized light from the black hole. Longer observing campaigns might help us catch and track individual features in the accretion flow. Some researchers are even exploring the possibility of space-based radio dishes that could link up with ground-based ones, creating an Earth-to-orbit array with much greater resolution. Each of these steps could answer one or more of the questions the first photo left hanging, but for now, the black hole at the heart of our galaxy remains partly hidden, both by the limits of our technology and by the nature of the object itself. Even with all our advances, a single image, no matter how groundbreaking, cannot capture the full story of our black hole. Could something be orbiting inside the event horizon? The inside of a black hole is less like an undiscovered country and more like a sealed box that can never be opened. Still, theories try to reach inside, using mathematics and the laws of physics as the only tools available. The simplest idea, drawn from classical physics, says that nothing orbits inside. Once matter crosses the event horizon, it moves inexorably toward the singularity, without the possibility of circling around it. In that picture, space and time themselves are so distorted that all paths lead inward. But modern physics does not stop at this stark conclusion. It asks whether the singularity is even real, or whether something else takes its place when quantum effects become important. One possibility comes from the idea of quantum gravity, where the known rules of gravity merge with those of quantum mechanics. In such a framework, the singularity might be replaced by an extremely dense but finite structure. It would be unimaginably small, far tinier than an atom, but it could hold all the mass and energy of the black hole in a strange quantum state. If that is true, then space inside the event horizon might have regions where particles or fields could, in theory, move in loops or patterns, although to us on the outside, these orbits would be hidden forever. Some researchers have imagined that inside a black hole there might be entire zones where physics behaves differently. In certain speculative models, once you pass the event horizon, you could encounter a kind of inner horizon, a second boundary that marks a transition to another kind of spacetime. Inside this region, it's possible, at least in mathematics, for particles or even light to move in stable paths. In such models, the singularity is not a simple point, but a complicated structure, sometimes shaped like a ring. In that scenario, orbiting inside is possible, but it would be nothing like orbits around a star or planet. Another idea comes from the concept of exotic matter, forms of matter that obey rules unlike anything we know from ordinary atoms. Some versions of string theory suggest the interior of a black hole could be filled with tangled networks of strings or membranes, each vibrating at different frequencies. Within such a bizarre environment, movement might not even follow the traditional curve of an orbit. Instead, objects could be trapped in repeating loops of space-time, moving forward and backward in ways that have no equivalent in our everyday experience. Quantum mechanics also introduces the possibility of virtual particles, brief appearances of particle pairs that wink in and out of existence in empty space. Near the event horizon, these virtual particles play a role in what is known as Hawking radiation, the theoretical process by which black holes can slowly lose mass over trillions of years. If virtual particles can appear just outside the horizon, could they also exist inside? If so, their fleeting lifespans and strange behavior could create complex interactions within the black hole's core. In such a picture, you might imagine a kind of seething invisible ocean where quantum fluctuations swirl in patterns we would call orbits if we could see them, but they are gone almost as soon as they appear. A more radical line of thought suggests that the inside of a black hole might not even be part of our universe in the traditional sense. Some models propose that when matter falls in, it is funneled into a completely new region of space and time, possibly even a new universe entirely. This leads to the wormhole idea, the notion that some black holes might connect to distant parts of our universe, or even to entirely separate universes. The mathematics for certain solutions of Einstein's equations allows for structures where matter could enter, follow curved paths inside, and then emerge somewhere else. If a wormhole were stable, which most physicists doubt, it might contain zones where movement looks like orbiting, but instead of circling a central mass, the objects would be winding through curved tunnels of space-time. There is a line of thought that focuses less on matter and more on information. Some researchers studying the black hole information paradox, the puzzle of whether information is destroyed when it falls into a black hole, suggest that information could be preserved in some form inside. If so, these patterns could, in theory, change and interact over time, forming cycles or repeating behaviors. In loop quantum gravity, a theory that tries to describe space and time as being made of tiny discrete units, space itself has a kind of atomic structure. Inside a black hole, these units might arrange themselves in such a way that instead of collapsing to a singularity, the matter bounces and oscillates. This bounce could lead to a dynamic interior where certain regions repeatedly swing around others. In such a model, orbits could be a byproduct of the geometry of space itself, not of gravity pulling on matter in the usual way. Some cosmologists have asked whether black holes might be seeds of new universes, with their interiors expanding in a way that is invisible to the outside. If so, the inside might look like a vast, expanding cosmos with its own stars and galaxies. From that point of view, our own universe might have begun inside a black hole in another universe. Of course, all of these ideas face the same ultimate barrier. The event horizon does not let us see inside. No matter how advanced our telescopes become, the interior will remain hidden from direct observation. The only way we can explore it is through mathematics, simulations, and indirect clues from how the black hole interacts with the space around it. But that does not stop scientists from asking the question, because sometimes the act of imagining what could be inside is as important as finding the answer. It forces us to test the limits of our theories and to think about the nature of space, time, and reality itself in ways we never would otherwise. Dark matter or dark shadow? The evidence that Sagittarius A-star is a supermassive black hole seems overwhelming. Stars whip around an invisible point at extreme speeds, their paths shaped by a gravitational pull that cannot be explained by ordinary matter. The light coming from nearby gas and dust matches what is expected from material being heated to extreme temperatures as it falls towards an event horizon. But in science, assumptions are always tested. And for something as strange and important as a black hole, alternative ideas have been put on the table. Some researchers have asked the question, what if Sagittarius A-star is not a black hole at all? What if it is something even stranger? The first alternative that comes up is dark matter. Dark matter doesn't emit, absorb, or reflect light, which makes it impossible to detect directly. We only know it's there because of its gravitational effects on galaxies and galaxy clusters. It holds cosmic structures together and makes up most of the matter in the universe, yet it remains unidentified. Could Sagittarius A-star be a massive concentration of dark matter? On the surface, it might seem plausible. Dark matter could, in theory, clump into a dense region at the center of the galaxy. Its gravity could still pull on stars in the same way we observe. But there's a problem. Dark matter does not seem to interact much with itself, and it does not lose energy by radiating heat or light the way normal matter does. Without a way to shed energy, it would not collapse into a small, dense core like we see in Sagittarius A-star. It would stay spread out. And our observations show that whatever is in the center of the Milky Way is incredibly compact. So compact that it fits inside a space smaller than our solar system. That's far too dense for any known form of dark matter to achieve. Still, some researchers have considered that maybe there are types of dark matter we haven't discovered yet. Particles that do interact with each other more strongly. If such particles existed, perhaps they could clump together into something as dense as a black hole without actually forming an event horizon. These hypothetical dark matter structures would be invisible, but they might not behave exactly like black holes. They could have a solid or fuzzy surface, and anything falling onto them would hit that surface rather than disappearing forever. The challenge is that no observation so far has shown signs of such a surface. Everything falling towards Sagittarius A-star seems to vanish completely from view, just as if it were crossing an event horizon. Another alternative idea is the boson star. This is one of the more exotic proposals, and it comes from the world of particle physics. Bosons are particles that follow different rules than the particles that make up normal matter. Photons, the particles of light, are bosons. The Higgs particle is a boson. Some theories suggest there could be a new kind of boson, ultralight and extremely stable, that could form gigantic clouds in space. Under the right conditions, such bosons could collapse into a very dense, star-like object without forming a black hole. A boson star would have no hard surface, but it also wouldn't have a true event horizon. Instead, light passing near it would bend in strange ways, and material falling toward it might slow down rather than disappearing completely. If Sagittarius A-star were a boson star, its image might look very similar to that of a black hole at the resolutions we currently have. The shadow in the famous photo could still appear because light would be bent and redirected around it, creating a dark central region. But there could be subtle differences in how the brightness changes over time, or in how matter moves close to the object. Detecting those differences would require sharper images and more precise timing measurements than we have today. Then there's the Gravitational, a concept born from attempts to avoid the singularity problem in black holes. Some physicists are deeply uncomfortable with infinities in their equations. In the late 1990s, the Gravitational idea was proposed as a way around this. Instead of collapsing into a singularity, the core of a dying star might go through a phase transition, like water turning into ice, creating a shell of exotic matter. Inside that shell, space would be filled with a strange form of energy, possibly the same kind that drives the expansion of the universe. From the outside, a gravastar would look almost exactly like a black hole. It would still bend light in the same way, and the orbits of stars around it would be indistinguishable from those around a true black hole. But there would be no event horizon, just a surface just barely beyond the point where light could escape. If Sagittarius A-star were a gravastar, falling material would not vanish forever. Instead, it might slam into the surface, releasing a sudden flash of energy. Detecting such a flash could prove the gravastar idea, but no such flash has ever been observed. One reason could be that the infall of matter is too steady and faint to produce a visible burst. Another is that our telescopes aren't sensitive enough to catch it. Either way, the gravastar remains in the category of possible but unproven. There are even wilder ideas. Some scientists have speculated about fuzzballs, which come from string theory and suggest that black holes might be made entirely of tangled strings of fundamental energy. In this view, there's no empty space inside a black hole and no singularity, just a messy ball of strings that from far away looks like a black hole. Others have proposed that black holes might be wormhole mouths. If that were the case, it would make the center of our galaxy a gateway. These ideas are almost entirely speculative, but they remain on the edges of theoretical discussion because black holes still leave us with so many unanswered questions. The problem with testing any of these alternatives is that, for all practical purposes, Sagittarius A-star behaves exactly like a black hole. Observations so far have been consistent with the black hole model, and none have shown a clear signal that would point to a boson star, gravastar, or any other exotic object. Yet, science works best when it keeps questioning, when it leaves room for possibilities that might at first seem unlikely. Each new observation brings us a little closer to seeing into the true nature of one of the most mysterious places in the galaxy. And until the evidence is so strong that all other possibilities fade away, the question will remain: are we certain about what's really hiding at the heart of the Milky Way? Or have we only begun to scratch the surface? How did Sagittarius A-star help shape the Milky Way? The Milky Way's central region is very different from the calm suburbs of the galaxy where our Sun resides. Stars near Sagittarius A-star move at incredible speeds, sometimes completing an orbit in just a few years. The gravitational field in this inner zone is intense, and this concentration of gravity could have influenced how matter collected in the earlier stages of the galaxy's life. When the Milky Way was young, over 13 billion years ago, it was not a smooth, elegant spiral. It was messy, filled with clumps of gas, dust, and small protogalaxies merging together. In those chaotic times, the seeds of today's structures were forming. Sagittarius A-star likely began as a much smaller black hole, perhaps the remnant of one of the first massive stars. Over time, as gas and stars fell toward the center, the black hole grew. Its gravity may have helped pull matter inward, deepening the central potential well, and encouraging the buildup of the dense bulge we see today. Simulations suggest that even in those early days, a central black hole could stir the surrounding gas. This movement of gas could have two very different effects. In some cases, it might funnel material toward the center, feeding the black hole and helping the bulge form faster. In other cases, if the black hole became active, it could blow gas outward, halting star formation in certain areas. Which effect dominates depends on how fast the black hole is growing and how much energy it releases. Astronomers have observed that many large galaxies have central black holes whose mass is directly related to the mass of the galaxy's bulge. This relationship suggests that black holes and bulges grow together. While this does not prove that Sagittarius A-star shaped the Milky Way, it hints that its growth and the galaxy's growth were connected in some way. If Sagittarius A-star did have a strong influence in the past, it likely happened during periods when it was much more active. In that state, it would have pumped huge amounts of energy into its surroundings. Such activity could have prevented certain areas from forming stars too quickly, allowing the spiral structure to evolve over a longer period. The Fermi bubbles show that the black hole's reach is not just local, it could affect the galaxy's halo as well. Events like that might have played a role in shaping the overall distribution of matter in the Milky Way. The gravitational pull of Sagittarius A-star is strongest close to the center, but it gradually fades with distance. However, the central mass concentration, including both the black hole and the dense star cluster around it, may have helped maintain the stability of the Milky Way's bar structure, a long, bright band of stars that cuts across the center and funnels material inward. This bar could be important for feeding gas into the inner regions, both for star formation and for the black hole's own growth. It is also possible that Sagittarius A-star influenced the Milky Way's chemical evolution. By controlling where and when stars formed, it could indirectly affect how heavy elements were spread through the galaxy. In places where the black hole's activity cleared out gas, star formation might have paused, delaying the recycling of elements like carbon, oxygen, and iron into new generations of stars. Over billions of years, this could contribute to the variety of chemical compositions we see in different parts of the galaxy today. Still, there are limits to how much impact a central black hole can have. The Milky Way is enormous, and its outer disk lies so far from Sagittarius A-star that its gravity is barely noticeable there. The spiral arms where the Sun resides are shaped more by the density waves moving through the disk than by anything happening at the core. This means that while Sagittarius A-star might have influenced the inner structure and bulge, the galaxy's sweeping arms likely developed through other processes. The early Milky Way has long since changed beyond recognition, and much of the evidence is buried in the motions and compositions of stars we observe today. By studying other galaxies at various stages of growth, researchers hope to find snapshots of what ours might have looked like billions of years ago, and in those snapshots, see the fingerprints of central black holes shaping their hosts. Some models suggest that without a central black hole, the Milky Way might have ended up with a very different appearance, perhaps with a smaller bulge or a less organized inner structure. Others argue that while black holes and galaxies do grow together, the black hole's influence is more of a feedback loop than a master plan. In this view, Sagittarius A-star shaped the Milky Way's heart, but the galaxy's overall form came from a mix of gravity, rotation, and the slow settling of matter over cosmic time. The truth may be somewhere in between. Sagittarius A-star was likely both a passenger and a driver in the Milky Way story. At times it may have been a quiet observer, letting the galaxy evolve naturally. At other times it may have sent ripples of energy and motion through the heart of the Milky Way, leaving marks we can still trace today. The next generation of black hole eyes. Around the world, engineers, astronomers, and computer scientists are working on the next stage of instruments that will make the EHT look like an early prototype. The picture of Sagittarius A-star we have today is the product of incredible cooperation. But it was also made with technology that is already years old. In astronomy, there is always a delay between the moment data is collected and the moment results are published. By the time the image of our galaxy's central black hole was released, the tools used to create it were already on their way to being improved. The biggest step forward will come from adding more telescopes to the network. The more stations you have, the sharper the image becomes. Right now, there are gaps in the virtual mirror of the EHT because you can only place telescopes in certain locations where the terrain, funding, and political agreements allow it. Adding new sites in parts of the world where there are no current EHT stations would fill in those gaps, giving astronomers a more complete view of Sagittarius A-star. One plan is to place new radio dishes in Africa, which would help cover the southern hemisphere sky more evenly. Another proposal involves installing additional stations in the Pacific Islands or even at sea, possibly on ships or floating platforms. These would catch parts of the radio wave patterns that current telescopes miss. Each new location increases the detail we can recover from the light around the black hole. There's also talk of moving some of these observatories into space. This is one of the most exciting possibilities. Space-based radio telescopes could orbit Earth or even travel farther out, creating a virtual dish larger than Earth. This space, VLBI, has been tested before, but not yet for something as challenging as imaging a black hole. A space-based dish working with ground-based telescopes could increase the resolution so much that we might be able to see changes in Sagittarius A-star's shape over just a few hours or days. Another major leap will come from improvements in the way the data is handled. The current EHT uses an enormous amount of data. Future systems will use faster, higher capacity recording and may even allow direct streaming between sites using ultra-high-speed connections. This would let astronomers combine and process the data in near real time, rather than waiting months for the results. Processing power is also getting a boost. The computers that turn the EHT's raw signals into an image are already impressive, but the next generation will use more advanced algorithms, some of them driven by machine learning. These systems can recognize patterns in the interference data faster and more accurately than human-made software, producing clearer, more reliable images. Artificial intelligence could also help detect changes in the black hole's surroundings more quickly, flagging interesting events as they happen. Even the way telescopes look at Sagittarius A-star will change. Right now, the EHT observes at a single radio wavelength of 1.3 millimeters. This is a sweet spot for passing through Earth's atmosphere with minimal interference, but it's only one slice of the spectrum. By observing at multiple wavelengths at once, astronomers could get more information about the material around the black hole, its temperature, and how different layers of gas and plasma move. The addition of shorter wavelengths, like 0.87 millimeters, would sharpen the image further, but also require extremely precise equipment to handle the smaller, more fragile signals. Longer wavelengths could reveal cooler gas farther from the event horizon, giving a fuller picture of the environment. The next phase of the EHT will likely include more of this multiband observing, essentially giving us color images of black holes, even though they won't look like colors to the human eye. Future instruments may also observe for longer stretches of time. The first EHT image of Sagittarius A-star was based on only a few nights of observations because all telescopes had to be in clear weather at the same time. New scheduling and weather prediction methods will help capture more data. The more we observe, the more we can track changes in the black hole's surroundings. This could lead to movies of material moving around Sagittarius A-star, showing the swirling plasma in motion. One of the most ambitious concepts is to combine the EHT with other types of telescopes entirely. For example, the upcoming square-kilometre array in Australia and South Africa will be the largest radio telescope ever built, covering huge areas with thousands of smaller antennas. While it's not designed specifically for imaging black holes at the EHT's resolution, it could be linked into the network to add sensitivity. That would allow fainter features to be detected, such as smaller flares or thin streams of plasma. In the far future, some astronomers dream about using telescopes placed on the Moon for EHT work. The Moon's lack of atmosphere would allow radio observations without the distortions that Earth's air creates, and telescopes there could operate around the clock, without the day-night cycle interrupting observations. A lunar station paired with Earth-based sites would make the virtual dish enormous, sharpening our view dramatically. The first image of M87 star included a polarization map showing the magnetic field lines around the black hole, and similar work is being done for Sagittarius A-star. Improved polarization data could reveal how these fields twist, break, and reconnect, offering clues about why Sagittarius A-star's relative quietness. New instruments will also make it easier to compare Sagittarius A-star to black holes in other galaxies. If we can get equally sharp images of multiple black holes, we can start to see patterns, whether size, spin, feeding rate, or magnetic activity determines their appearance and behavior. The EHT's first picture was a milestone, but it is almost certain to be replaced by a clearer, sharper image before long. If the upgrades succeed, the next generation of black hole imagers will not just show us a still frame. They will let us watch our galaxy's most mysterious object in action. X-ray polarimetry and the secret of spin. The speed of Sagittarius A-star's spin could tell us a great deal about its history, whether it grew slowly by eating small bits of matter over billions of years, or whether it gulped down large amounts all at once, possibly in violent mergers with other black holes. The problem is, spin is not something we can see directly. We have to infer it from the way light and matter behave near the black hole. And one of the most promising ways to do that is through a method called X-ray polarimetry. Polarimetry measures the orientation of light waves. Light is made up of electromagnetic waves that can vibrate in many directions. But certain physical processes, such as scattering off particles or moving through magnetic fields, can cause those vibrations to align in particular ways. When we measure that alignment, we gain clues about the environment the light has passed through. In the case of Sagittarius A-star, we're interested in the polarization of X-rays emitted from matter as it spirals into the black hole. These high-energy photons can carry the fingerprints of the black hole's spin, hidden in their polarization patterns. Matter falling towards Sagittarius A-star heats up, producing X-rays. These X-rays bounce around in the warped space near the event horizon, influenced by both gravity and magnetic fields. If the black hole is spinning, it drags space itself around with it, a phenomenon called frame dragging. This twisting of space-time changes the paths the X-rays take, how they scatter, and how their electric fields are oriented when they finally escape to us. By studying exactly how polarized these X-rays are, we can backtrack and determine not only the geometry of the material swirling in, but also the black hole's spin rate. Up until recently, X-ray polarimetry was a dream more than a reality. While we've been able to measure X-rays for decades, measuring their polarization is much harder. The instruments need to detect not just the energy and direction of each photon, but also the orientation of its electric field. This requires incredibly sensitive detectors and very stable platforms. On Earth, X-rays from space are absorbed by the atmosphere, so polarimetry must be done from above the air, either from satellites or high-altitude balloons. NASA's Imaging X-ray Polarimetry Explorer, or IXPE, launched in December 2021, is one of the first dedicated missions for this purpose. IXPE is already collecting polarization data on various cosmic objects, pulsars, supernova remnants, and distant active galaxies. Sagittarius A-star is a challenging target because it's relatively faint in X-rays compared to more active black holes. But IXPE has the precision to attempt it during flares. In those brief moments, the polarization signal could be strong enough to give us a reading. Concepts for the next generation include instruments with larger collecting areas to gather more X-ray photons, higher resolution to separate the black hole's emission from the crowded galactic center, and faster timing capabilities to track changes in polarization during a flare in real time. These improvements could allow us to watch the polarization angles swing as matter orbits near the event horizon, an effect that could reveal not only spin, but also the tilt of the black hole's rotation axis relative to the galaxy. A fast-spinning black hole can store enormous amounts of rotational energy, which can be tapped to power jets and winds. Even though Sagittarius A-star doesn't have a major jet today, its spin might still be a hidden engine, influencing the dynamics of the gas around it. The spin could also be a fossil record of past events. If the spin is high and aligned with the galactic plane, it might mean Sagittarius A-star grew mostly by pulling in matter from the galaxy's disk. If the spin is low or tilted at a strange angle, it might mean it was involved in chaotic mergers, swallowing other black holes that came in from odd directions. There is also the question of whether spin can change over time. If Sagittarius A-star is about to enter a more active phase, as some recent flaring behavior suggests, new infalling material could either spin it up or slow it down, depending on the direction of its angular momentum. Polarimetry offers a way to track this evolution over years or decades, turning spin from a fixed property into a dynamic measurement. Spin measurements also feed into our understanding of general relativity in the strong gravity regime. Einstein's equations make specific predictions about how a spinning black hole warps spacetime and polarizes light. If polarimetry results disagree with those predictions, it could signal new physics. Perhaps the geometry near the event horizon isn't exactly what general relativity describes, or perhaps quantum effects are playing a role. Another interesting twist is that polarization could help separate the effects of gravity from those of magnetic fields. Near a black hole, these two influences are intertwined. The gas spiraling in carries magnetic fields with it, and those fields can twist, reconnect, and release energy. Magnetic fields can also polarize light, but in a different way than gravity does. By comparing polarization at different X-ray energies, scientists can try to disentangle the two effects, leading to a clearer picture of the black hole's environment. Long-term, we might even see interferometric X-ray polarimetry. This could give us polarization maps at extremely fine resolution, perhaps showing which parts of the accretion flow contribute most to the signal. For Sagittarius A-star, that could mean identifying where the flare's X-rays are actually coming from, a hotspot orbiting close to the event horizon, a shock front in the accretion flow, or some magnetic reconnection event. As the tech advances, polarimetry may become as routine as measuring brightness or spectrum. For now, though, it is on the cutting edge, a technique that could open a new dimension in our study of black holes. In the case of Sagittarius A-star, it offers a rare and precise way to peer into its hidden history. We may not be able to send a probe into the black hole, but by studying the subtle patterns of X-ray polarization, we might read the story written in the twists of spacetime. Gravitational waves from the center, a stable black hole like Sagittarius A-star, one that isn't merging with another object, doesn't create gravitational waves that are strong enough for us to detect. The space around it is distorted, yes, but it's not changing fast enough to produce ripples we can pick up. For gravitational waves to be generated in a way we could measure, something dramatic has to happen. That might mean a smaller black hole spiraling into Sagittarius A-star, or a massive star being torn apart. or even two black holes merging in the galactic center. One of the most promising scenarios is what scientists call an extreme mass ratio in spiral, or EMRI. This is when a much smaller object, like a star or a black hole, a few tens of times the Sun's mass, gets caught in the gravitational grip of Sagittarius A-star and slowly spirals inward over thousands or even millions of years. As it falls closer, it moves faster, and the distortions in space-time grow more intense. Near the end, in the final years or months before it crosses the event horizon, the smaller object would produce gravitational waves with a signature unlike anything else in the universe. These signals would be too low in frequency for our current ground-based detectors like LIGO or Virgo to pick up, because their mirrors and lasers are tuned for higher frequency events like stellar mass black hole collisions. But a future space-based gravitational wave observatory, such as the European Space Agency's planned LISA mission, would be able to hear them. LISA, short for Laser Interferometer Space Antenna, is designed to detect gravitational waves in the millihertz range, exactly the kind of slow, deep rumble that an EMRI would produce as a small object falls into a supermassive black hole. Instead of using mirrors on Earth, LISA will have 3 spacecraft placed millions of kilometers apart in space, linked by laser beams. This huge separation allows it to sense the long, drawn-out distortions caused by massive objects orbiting each other slowly. If a stellar mass black hole or neutron star is ever caught in the death spiral towards Sagittarius A-star, LISA could, in theory, detect it years before the final plunge. That would give astronomers time to prepare and coordinate observations with telescopes across the spectrum, from radio to X-rays, to watch the drama unfold. There's also the possibility of detecting gravitational waves from more exotic events, such as a sudden collapse of a massive star into a black hole near the galactic center, or the shattering of a neutron star under extreme tidal forces. These would be short-lived but extremely violent, producing high-frequency waves that our current detectors could pick up. However, these events are rare and unpredictable, and we'd have to be extraordinarily lucky for one to occur close enough to Sagittarius A-star while our instruments are running. If we could detect gravitational waves from Sagittarius A-star, the scientific payoff would be enormous. We could measure its mass and spin with incredible accuracy, far beyond what is possible using light alone. We could also test general relativity in the strongest gravitational field accessible to us. If the signals showed any deviation from what the theory predicts, it could point to new physics, perhaps even revealing something unexpected about the nature of space-time near the event horizon. One particularly intriguing aspect is that gravitational waves could give us a direct sense of what's happening in the region immediately outside the event horizon, without being blocked by gas, dust, or magnetic fields. Light can be scattered, absorbed, or distorted, but gravitational waves pass through matter almost unaffected. This means that if we want a clean, unfiltered view of how Sagittarius A-star interacts with its surroundings, gravitational waves could become one of our most important tools. Detecting gravitational waves from such events requires not only highly sensitive instruments, but also years of continuous observation. The signals are often buried in noise and can last for months or years, requiring precise data analysis to extract them. The timing has to be perfect, especially if we want to coordinate gravitational wave detections with traditional telescope observations. This is why projects like LISA are planned for the 2030s or later. There's a lot of engineering and testing to be done before we can operate such a delicate instrument in space. Ground-based detectors are also being upgraded. The next generations, like Cosmic Explorer in the United States and the Einstein Telescope in Europe, aim to be more sensitive than anything we have today. While they won't be able to catch the slow in spirals into Sagittarius A-star, they could detect shorter bursts from sudden massive disruptions near the galactic center. Combining their data with space-based detectors could give us a complete picture, covering both the low and high-frequency ends of the gravitational wave spectrum. Looking ahead, it's possible that one day, we'll have a network of gravitational wave observatories in space, much like how radio astronomers use the VLBI method to link telescopes across the Earth. With multiple space-based detectors positioned at different points in the solar system, we could triangulate the source of waves with incredible precision, pinpointing exactly where in the galaxy they come from. That would make it possible to target Sagittarius A-star in real time with optical, infrared, and X-ray telescopes whenever something unusual happens. The idea of listening to the heartbeat of the Milky Way's central black hole is still in the realm of the future, but it's no longer pure science fiction. The technology is being developed, and the first steps toward detecting such signals are already underway. If and when that day comes, we won't just be seeing Sagittarius A-star through the lens of light. We'll be feeling its movements through the subtle tremors it sends across the fabric of the universe. When Andromeda meets the monster. In the far future, a great cosmic event awaits our galaxy. In about 4 billion years, the Milky Way will meet the Andromeda galaxy. The two are moving toward each other at a speed of roughly 110 kilometers per second. On human scales, that speed is extraordinary, but in the vastness of space, this slow drift is enough to set up one of the most dramatic events in galactic history. At the heart of this future encounter will be two supermassive black holes, Sagittarius A-star in our galaxy, and the black hole at the center of Andromeda, known as M31 star. When we think about a collision between galaxies, it's tempting to imagine stars smashing into each other like billiard balls. But stars are so far apart that even in a violent merger, almost all of them will pass by without direct contact. The true drama will be in the way gravity rearranges everything. The sweeping arcs of gas clouds, the twisting of spiral arms, the disruption of stellar orbits, and the slow but unstoppable migration of each galaxy's central black hole toward the other. Over millions of years, these two titans will be drawn together, falling toward each other through a process called dynamical friction. This is where the background of stars and dark matter acts like a drag, robbing the black holes of momentum until they spiral inward. Sagittarius A-star will not stay passive during this process. The influx of gas, dust, and disrupted stars from the collision will be like fuel pouring into its surroundings. The same will happen to Andromeda's black hole. Both could flare into active galactic nuclei, outshining entire galaxies, with the radiation from matter falling toward their event horizons. If this happens, the night skies of any worlds still present in the merging galaxies could be lit by two blazing points in the cosmic core, each far brighter than any star. The structure of the Milky Way will not survive intact. As the galaxies merge, their disks will be stretched, pulled, and eventually transformed into something new, likely an elliptical galaxy with less defined arms and a more spherical distribution of stars. The stars that once orbited in neat, nearly circular paths around the Milky Way's center will be thrown into random orbits, some ejected entirely into intergalactic space. For planets around certain stars, the gravitational chaos might dislodge them from their home systems, turning them into lonely wanderers drifting between galaxies. In the center, the slow dance between Sagittarius A-star and M31 star will continue, drawing closer with every orbit. For tens of millions of years, they will orbit each other at decreasing distances, sending gravitational waves that would be detectable by instruments far more sensitive than anything we have today. These waves would carry away energy, causing the pair to spiral inward faster and faster. In their final approach, the two event horizons will meet and merge in a burst of gravitational energy unlike anything our galaxy has ever known. This merger will not only reshape the core of the new galaxy, but also give it a single, even more massive black hole. The final mass could be tens of millions of times greater than our Sun, perhaps even approaching 100 million solar masses, depending on how much matter falls in during the process. The spin of this new black hole will be set by the orbital motion and spins of the two original giants, meaning the entire history of both galaxies will be written into the way this monster rotates. For life, If it still exists anywhere within the combined galaxy, the impact will depend heavily on distance from the center. Close to the merging black holes, the radiation from the infalling matter could sterilize planets or strip away atmospheres. But further out, where most stars will end up, the changes might be more subtle. Altered night skies, shifted constellations, and the gradual fading of spiral patterns that once defined each galaxy's beauty. Even though this collision will be far in the future, astronomers already study galaxy mergers happening elsewhere in the universe to get a preview of our own fate. Telescopes have captured images of galaxies in various stages of merging, from the first gentle tug of gravity to the final coalescence into a single shape. These cosmic snapshots tell us that the process is slow, taking hundreds of millions of years from first contact to complete union. It is less a crash and more a cosmic blending, with the two galaxies becoming ever more entangled until they are inseparable. Simulations suggest that our Sun, assuming it has not yet expanded into a red giant and destroyed the Earth, may end up in a completely different part of the merged galaxy. It could be flung to the outskirts, far from the core, or it could drift inward, depending on the gravitational interactions it experiences during the merger. Either way, the galaxy we call home will be unrecognizable, and its central black hole will no longer be the familiar Sagittarius A-star, but a far larger and more powerful descendant. The Andromeda collision will be one of the few events capable of waking Sagittarius A-star from its current quiet state for a truly extended period. The sheer volume of material funneling toward the center will ensure a long-lasting phase of high activity. Jets of high-energy particles could erupt from its poles, powered by the twisting magnetic fields around its accretion disk. The brightness in X-rays, radio waves, and visible light could spike to levels that would make the center of the galaxy an overwhelming beacon. From a cosmic perspective, this is not a destructive end, but a natural evolution. Galaxies grow by merging. The Milky Way itself is the product of countless earlier collisions, though most were with much smaller companions. The meeting with Andromeda is simply the next step, on a much grander scale. Sagittarius A-star has already survived billions of years of galactic history. In 4 billion more, it will take part in one of the most spectacular transformations in the universe, binding two vast star systems into one. Will Earth still exist to witness it? When the Milky Way and Andromeda collide in 4 billion years, and their black holes spiral into one another in a dramatic finale, will there be anyone here on Earth to actually see it happen? 4 billion years is an unimaginably long time. For perspective, that is almost the same amount of time that has passed since life first appeared on Earth. Over such a span, the Earth's position in space will not be fixed, and neither will the Sun's behavior remain constant. Our star is slowly growing brighter over time, a natural part of its life cycle. In another 1 to 2 billion years, it is expected that the Sun's increased energy output will cause Earth's climate to change in extreme ways. Oceans may begin to evaporate, the atmosphere could lose water to space, and surface conditions could grow too harsh for life as we know it. Long before the galaxies collide, our planet may have already lost its habitability. Even without the Sun's changes, the gravitational reshaping of the Milky Way during the collision will scatter stars into new orbits. The solar system is likely to be tossed into a different position within the merged galaxy. We may be pulled closer to the galactic core, where radiation and gravitational disturbances are stronger, or we might be pushed farther into the outskirts. These shifts could change the long-term stability of Earth's orbit. In the best-case scenario, the solar system remains relatively untouched, just drifting into a new neighborhood in the stars. In the worst case, interactions with passing stars could nudge planets into new paths, or even fling them into interstellar space. The process of galactic collision itself does not mean planets will smash into one another. Instead, the danger comes from the gravitational tug-of-war, as the two galaxies pass through each other multiple times before fully merging. Every close pass rearranges the orbits of countless stars. If our solar system is unlucky enough to be near the path of another star during one of these passes, even a slight change in gravity could disturb the delicate balance that keeps Earth circling the Sun. If Earth was somehow sent drifting into interstellar space, cut off from the Sun's warmth, it would become a frozen, airless world almost immediately. The only heat would come from the planet's interior, slowly radiating away into the darkness. Life, if any still existed, would be confined deep underground near geothermal vents. From such a world, the galaxy's collision might be visible as a slow-motion ballet of light in the sky, but no one on the surface would see it. In around 5 billion years, the Sun will exhaust the hydrogen fuel in its core and swell into a red giant. When that happens, its outer layers could engulf Mercury and Venus, and possibly Earth as well. Even if our planet avoids being swallowed, the sheer heat and radiation would destroy its surface and atmosphere. By the time the Milky Way's central black hole merges with Andromeda's, our Sun may already have transformed into a white dwarf, leaving Earth a scorched and lifeless husk. Humanity has only been here for a tiny fraction of Earth's history, and it is impossible to know whether any intelligent descendants, human or otherwise, will remain billions of years from now. Civilizations rise and fall on the scale of thousands of years, and the survival of life on Earth depends on countless factors. Humanity, or whatever species replaces us, might have spread to other planets, other star systems, even other galaxies. If that is the case, then the witnesses to the galactic collision and the final merging of the black holes may not be standing on Earth at all. Still, there is a slim chance that Earth itself could remain in a stable orbit and avoid the worst effects of both the Sun's evolution and the gravitational chaos of the galactic merger. In that rare outcome, the night sky during the collision would be unimaginably beautiful. Over millions of years, Andromeda would grow larger and brighter, eventually filling much of the sky with a haze of stars, glowing gas, and dark dust lanes. The sight would be breathtaking, no telescope needed. When the two galaxies fully merge, the view might be a tapestry of light stretching from horizon to horizon, the merged core shining brilliantly where Sagittarius A-star and Andromeda's black hole whirl toward each other. The black holes themselves would be hidden by vast clouds of gas and dust, but their influence could still be seen in the form of powerful jets and bursts of energy as matter spiraled toward them. These outbursts might briefly outshine every star in the galaxy combined. The night sky would not just be beautiful, it would be dynamic, changing over thousands of years as the cosmic dance reached its climax. The collision would also trigger waves of star formation throughout the merged galaxy, lighting up the night sky with clusters of newborn stars. From the ground, the heavens could look like a celebration in slow motion, a grand display lasting far longer than any single human lifetime. But the possibility remains that no one will be here to see it, not even microbes. Earth's long-term habitability is not guaranteed, and in the deep future, the forces that shape planets and stars will not wait for us. The galaxy will collide, the black holes will merge, and the universe will carry on, whether Earth is still spinning or not. If Earth does remain, it will bear silent witness to one of the most spectacular shows in the history of the cosmos. A front-row seat to the day when two galaxies become one, and when the monster at the center of ours finally meets its match. And now our journey comes to an end. Leave a comment on what topic you'd like to hear about next. If you enjoyed this voyage, consider leaving a like and subscribing to the channel. Thanks for watching.